says I'm live. Hopefully I'm live, and hopefully the stream stays up this time. Well, it went all right last week. Went all right. So hopefully tonight is going to be good as well. Welcome everybody. Sorry for the late notice. Decided to do this last minute, so yeah. Hopefully we can have a little bit of fun. I'll wait until some people say hello and everything before we really get into things. Give some people time to join. Hope everybody's been having a good week. I hope everybody is sort of come over the shock. All the big news this week. Our friendly Unity deciding to do all sorts of crazy things, and yeah, that was fun. So yeah, for those here who are new and joining from Unity, welcome. I'm not sure if there's many of you here, but I recognize one or two names in the chat from people that I've talked to over the past couple of days. I really hope that people in the end turn out not to be as affected as everybody worries. But if not, then I'm pretty sure we'll find a way forward. And be it as may, even if everybody nicely stays with Unity, all good. At least you get to know that there's something called Godot, and that there's this crazy dude doing XR stuff and rendering stuff, and yeah. Stefan, yes, you can press the what's it on YouTube, the super chat button, and you can donate 20 cents to me. So fun stuff. All right. Now, it has been a crazy week. A lot of people onboarding on XR. That's been a lot of fun. A lot of new faces, a lot of new projects that have popped up, including projects that were already started before all the craziness started. So, yeah, Chris, you're more than welcome. It's been interesting. It's been interesting to see a couple of problems that we are kind of not aware of anymore, because most of us have been on this journey for a couple of years now. So to have a lot of new people come in and suddenly run into problems that we actually don't even realize are there, that's been pretty good. And part of that, of course, also is people coming in there with a very different view on things, different expectations. And especially, there's still a few things to round off documentation-wise, so it's been really interesting. Welcome, Sin. Yes, very good. Another Unity person who has popped into Godot. So yeah, hopefully you guys like what you're finding and like what you're seeing. It's an interesting little engine. It has its quirks, but it's a lot of fun working with. So yeah, hopefully everybody has got good impressions so far. I'm looking at the right from time to time, by the way, because that's where my screen is with the chat. So it's not that actually my camera's in a bit of a weird place. So I've ordered a new camera that I can actually put near my screen, so that actually I'm looking at my camera when I'm working. So yeah. Anyway, for those who are new, my streams are pretty open forum. Hey Adam, how you going? I tend to just work on stuff and talk about what I'm working on and talk about what I'm looking at, and try to engage with chat, anybody who has got questions. The plan for tonight is to have a look at rendering effects. So that's a little bit hardcore. That's very low level stuff in the engine. But I'm hoping actually to implement something tonight, or to try something out as a sort of start to a more higher level implementation of this, built on top of the lower level implementation, so that a lot of things are just taken care of, instead of you needing to know a lot about the rendering engine in order to use this more efficiently. So that's the plan for tonight, but we'll see where things go. Again, if there are questions, or even questions unrelated to what we're discussing, I don't mind going off on a tangent from time to time. We'll just see where we end, and See if we can do it in I don't know, maybe 2 to 3 hours in total. That's the goal. It's late here, so obviously at some point in time I'm going to have to call it a night. But yeah, let's see how far we get. So the thing that we're going to be talking about is Rendering Effects, which is a system that Juan originally spec'd out and that I have implemented over the last month. And basically the idea of Render Effects is that we have a number of callbacks that we've added into the core of the rendering engine that trigger at specific points in the rendering pipeline that allow you to add additional logic into the rendering pipeline. It's a feature that's only fully implemented on the Forward Plus renderer. We have some basic functionality on the mobile renderer, but with the mobile renderer, it's very easy to get into trouble with these sort of things because of the tile-based architecture of mobile devices. We may implement this on the compatibility renderer after the Forward Plus things are merged as a next step to this. No promises on that. That depends a bit on whether we have the time for it. But that will be much more limited than what we're doing in the Forward Plus renderer. In the Forward Plus renderer, you really have a lot of places where you can start injecting logic, and it doesn't just have to be rendering logic. It could be that you do modifications to object buffers and things like that. This can grow into something very huge. But where most people will very likely use this for, and where the name also comes from, is for post effects. So using the last callback that we implemented, which happens right after the transparent pass renders, so that you can insert additional post effects. And that's also the sort of examples that so far we've made with this. So some of the other callbacks that we introduced, right now they're a little bit more limited to what is actually what you can actually do with them, because a good example, for instance, is that we very often will build or build data from the def buffer really early on so that that can run in parallel with the rest of the rendering, and then you pick it up in post effects and do something with it. So again, that is that. Hey Nab, how you going? And Sin, yes, I'm guessing that it is in the same line of that sort of functionality. I know that Unity has something similar, but similar in concept, I guess. So yeah, like I said at the beginning, it's fairly low level, so you do need to have some in-depth knowledge of how the renderer works in order to make good use of this. Although the more examples are there, the easier it sort of becomes to pick up and start running with things. There have already been a few people who have started playing with this and even done some streams or given some examples, and who sort of have pieced together stuff from what I have. Hiya, Brian. Oh, Ireland. That's really on the other side for me. So welcome. Okay, so take note of the PR. So obviously this is not merged yet. If you want to do and play around with this, if you follow along or play around with this, you do have to build Godot from source. But I suspect that this will be merged quite soon, unless someone finds something really structurally wrong with it. I think that the base level logic is there and ready to be merged, and for people to start playing with it, and then hopefully out of that a number of enhancements will follow. In the whole history of the project, you'll see that there's a couple of examples. So I started off with a very simple grayscale example, and as you can see, yes, the render effects do work in the editor. Although there are some timing issues there. So once you have a rendering effect finished, it works pretty well, but as you're building it, can get in the way a little bit. You sometimes have to restart the editor before things are picked up, and that's because it is rendering stuff. You're creating a bunch of things that are cached at that point in time, and they're harder to just sort of change and for the editor to change with it. So what else did I want to point out in the history? Yeah, so Kebab Skull, probably butchered his name there. He's one of the users who did a stream trying to reverse engineer what I was doing to try and figure out how he could build an effect, and he got it working. He did a really cool pixelation effect. But yeah, there were a few things that he ran into that he sort of went like, "Why is it so difficult?" And we sort of got out because this is a low-level implementation. We're probably going to put some things on top of it. But he got there in the end, which is really cool. So I don't think there's any... Oh yeah, here is... I guess that's the Unity version of it that was mentioned a minute ago. Hey, Drensoft, how you going? Yeah, it's been a while. I haven't been streaming much. I'm hoping to really pick up streaming again. So hopefully I can do this more often. They will stay very last minute. But I do hope to at some point do streaming again on a fixed day. That is the plan. Okay, Stefan. So for something like grayscale, nothing. Whether you do a grayscale effect with a full screen transparent, well, you would probably, that's the only difference, I guess. If right now you would do it with a full screen quad during the transparent pass, and you would read from screen texture, which means that Godot needs to make a copy of the screen, and then you read from that copy, do your grayscale modification, and write back into the normal buffer, which is wasteful. With the render effects, because you can actually insert a new pass, and you can insert a compute shader pass if that's the direction that you want to go, which you would in this case. You can actually do the modification on the buffer itself, which obviously saves a bunch of performance. But for more complex changes, like I'll show in a minute, those are things that you just can't do in the normal rendering pipeline. So, for instance, I can quickly show. I hope this comes across well on stream and that the stream quality doesn't filter it out. But this is a Godot Ray implementation that uses render effects, where you can see that the sun sort of creates rays through the through everything being obscured by the tree here. So yeah, this was a little cool thing that I made after QB mentioned. Forgot his name. There's this a guy on Twitter and YouTube who does a lot of render effects and post effects implementation. I think he usually does stuff in Unity. That's some very impressive stuff, but he explains in depth how he does things. And he explained this. This is a fairly old effect. But he explained it, and QB sort of went like, "Baz, can we do this?" I said, "Probably." So I put this together as a sort of proof of concept. I am by no means a graphics artist. I'm just a programmer. So I'm pretty sure that that someone with a bit more eye for that sort of stuff would probably pick this up and improve it quite a bit. But as a quick implementation, it's a really good example. So this was also then an example that is on my GitHub. So if you go to my GitHub page, Bastien LA on GitHub, you'll find a project called RE Radial Sunrays, and you can just grab a copy of that project, and you can go and have a look at the code and see how I've done this. Well, actually, we'll take a quick look at the code here to see how it all works. And I need a drink first before we do that. For some reason, after a long and cold winter, we just moved into spring, and Australia decided to give us a heat wave right away. So it is hot at the moment. So I'll be drinking plenty of fluids during stream tonight. I hope that my bottle doesn't run out before the stream ends. All right. So all the magic happens in this folder called Radial Sky Rays, and what you can see there is a number of GLSL files. So that's obviously shader code. Now here is one weakness at the solution at this point in time, and this has actually not got anything to do with rendering effects. This has got to do with the GLSL pipeline in Godot. You can't actually edit this. When you double click on it, you get this this tester thing that tests whether your shader can be compiled. But we need to edit the files behind the scenes. So let's see if it's still in my history. Yes, it is. So when we want to have a look at the actual shader code, we'll jump quickly into VS Code and make the changes there, or in this case, look at the code. The render effect itself is implemented in a GDScript file. It's all based on subclassing or extending the class render effects. So obviously you can implement this anywhere you want. If you want to implement this in GD extensions in C++, you can put this code in C++. You can do it in GDScript like I've done here. You can do it in C#. Whatever you fancy, it doesn't really matter. Godot doesn't care. As long as it's a render effect that is being implemented, it's going to be happy and it's going to run it. So 7, that's pretty much the conclusion, yes. So yeah, pretty much it just allows you to do to implement a full render pass. Actually, this one is actually multiple passes that we chain, and it's just something that you can't do in the normal pipeline, or you could do it with viewports, but that's very inefficient. I've seen some people do some really interesting things that way, but there's a lot of overhead and problems with that. Rendering effects gives you a lot more freedom in what you want to do. I hope that the font is readable, that the text is readable. If not, please let me know. I can probably zoom it in a bit. Excuse me. But basically, as the introduction here describes, we're doing this process in 4 steps. So we're starting off with this first step, where when we're looking at our image here, we're basically in a depth, using a depth buffer, we are rendering the sun that we have over here to a separate image. And obviously the depth buffer is then used to obscure the sun so that only the part of the sun, actually, hold on, let me go and start this little guy. So yeah, I know, because I just used the meta version of this thing. That is not the one that I want to test with. Where are you? Where can I see what my folder is? That sucks. I probably can. No, I closed that. That's done. Okay. It should be RE Radial Sun Rays launch. Ka-ching! Capture. So this is Renderdoc for people who don't look at things that are behind the scenes. Renderdoc is this really, really cool and free application that allows you to investigate what your GPU is doing when a rendering engine is doing its work. And I just told it to capture a single frame. And basically we get all the instructions shown that render a single frame in Godot. And the nice thing that we do in Godot is we add additional information so that everything's nicely grouped and broken up and stuff, which is kind of cool. And we'll see in a minute in the code how we actually do that, because we have a nice little entry here called Radial Sky Rays, and guess what? That's where all our steps are being done. So we were just talking about the rendering of the sun disk, and when I click on that, I can actually see what's happening here. And in this case, my inputs is my depth buffer. So here we can see the depth buffer that was rendered during our normal render. And what we're outputting is well, it turns red, but it's actually a single color image. We render this nice little, well, disk circle for our sun, but it's obscured by anything that's in the foreground. So our depth buffer is used to kind of cut out the sun. So that's a first step. So if we look at our code here, we'll go through a bunch of these things in a minute, but I just want to go to the heart of the code, which is this function called render callback. So at a given time, and we'll talk a bit more about that in a minute as well. In this case, right after the transparent, actually we can see the constant here because we double check for this. We've configured this to work on the transparent pass, but it is possible that you could have a render effect that you want to implement as a single effect, but that you add multiple times because you want to run it at different parts. And then you can check, at which part we're calling it at this moment. It's one of the choices that you have. But we verify that that we're being called during our post-transparent pass. So transparent rendering is done. Godot has nicely finished off its work, and we get in here. Now there's some setup that we need to do here. I'm going to go back to that as well. I want to go to the heart of what we're doing here. Do note here our draw command begin label. That is what we saw here, which is our radial sky. And then we're going to see in a minute that when we render our sun disk, that we again do a draw command begin label, which nests our extra process. So that makes it nice and easy to debug things. All these sort of things are automatically filtered out when you export a runtime version of your game. So this is purely a debugging tool for for people like us who are working on the rendering engine, but also when you do something like post effects, it helps a lot to get those moments in there, so that if you use a tool like Renderdoc to see if what you're doing actually happens, because that's really what this tool is really good at. But if something doesn't seem to happen on the screen, this is the tool that can show you behind the scenes, is your shader running? Are you using the wrong textures? Are you mixing things up? Really brilliant. Highly recommend getting a hang of it if you want to work on that level. But this is basically the whole setup of one step. So what we're seeing here is that we are defining two uniforms, or actually uniform sets. We could create a single set and combine them, but in this case, they are two. These are mirrored in our shader. We'll see that in a minute when we look at the shader code. But we have a uniform set for our input. Remember when we were looking here that we had our depth buffer as our input. So we're grabbing that one. I grabbed that up here, by the way. So I'll talk about the different objects that we have access to later on, but we're getting our depth buffer over here, and that's the one that we now use. And we are grabbing a thing called texture image, and that's one that is going to deserve some more explanation. But basically, that is a buffer. That's our output buffer here that we created specifically for this effect. So that's not a buffer that Godot created. That's not a buffer that is part of our rendering engine. That's a part that a buffer that I have created for this specific effect. And the way that Godot works, because those buffers are only usable as long as everything stays the same. So if I resize my window, I need new buffers, that sort of thing. And Godot has this caching cleanup system behind it that if you look at the code, I'm simply checking, do I have the texture that I'm after? And if not, I'm going to create a texture. Now, I've actually created two, because in later effects, I need to do a ping pong. I need to take what I last written into that buffer as input for the next stage, and I'm writing out in another buffer because I can't overwrite my input buffer, because then the effect falls apart. So that's why I create two of them. We'll see in a minute that we start flipping those around, which is kind of nice. Now, the great thing about this is I don't need to do any cleanup here, and I don't need to do any testing here. If something changes, the user resizes the screen, or a certain effect is enabled that does something, let's say that I turn MSAA on or something like that. Godot automatically cleans up, and the next time that I come in here, I can see that, hey, I no longer have buffers. I again have to tell it, go and create those because I want to use them. And then here we can see that we're actually picking them up. So we're grabbing our texture image for our normal image and then also for our Pong image. And then we can later on use those. So those are our two inputs, a uniform set for our def buffer and a uniform set for our output buffer, our little temporary buffer that we created. The next thing that we are doing is we are building what is called a push constant. So a push constant is a little bit of memory that can be no more than 128 bytes, I think, for memory, something like that, that you can use as input into your shader. So this is a great way to send some simple settings through. You can do the same thing through uniforms. So you can create a uniform buffer and you can put a bunch of data in there and then you can upload that and use that in your shader. This is a tiny version of that is much simpler to set up. So you just load some data in there and you then sending your doing your pass, you're saying, here you go, push constant, here's a little bit of data, I want to use this, that's it. The problem that we right now have is that you can build a complete struct on the shader side, and we're going to see that on the shader in a minute. But on the Godot side right now, we don't have struct support yet. It's being worked on. We don't have it yet. So what you can see is that I'm simply making a float array and putting my float variables in there. And some of these are actually integers, but I'm converting them to float, pushing them over as floats and using them as floats on the other side. Something to be improved in the future, but for now this works. Hey, this is Alex. How you going? Yep, we're doing render effects for a change. Something else than XR for night. Hey, Kyle, let's see. Will it allow us to render directly into the scene with the rendering device? Yes, that's basically what we're doing. Is we're inserting at given points during the rendering pipeline, we're getting the chance to do something extra. So in this case, I'm doing it all the way at the end after the transparent pass, and I'm using the buffers that Godot is using to apply these effects. So in this case, just to recap, we are talking about the very first step where we're taking our def buffer. Hello, def buffer. That's the def buffer that Godot has in flight. That's the one that we just created during rendering. And I'm currently outputting to one of my own buffers in which I want to, this is a grayscale buffer. It's actually, what did I make it? I made it a 16-bit unorm floating point buffer. So that means that we have values between 0 and 1. Minus 1 and 1. No, I think it's 0 and 1. Don't hold that one against me if I don't think it's signed. I think it's unsigned. Yeah, unsigned normalized. So it's a buffer value between 0 and 1, and it's stored as a 16-bit float. That's for every pixel. So so that's the buffer that we're using here. And therefore, that's why it's red, because I'm just getting the red channel. That's the first channel in our thing, so everything's red. But it's actually a full grayscale image. And all that I'm doing in that first step is I'm drawing a circle for my sun and checking the def buffer while I'm doing that. And obviously, if there's something in front of my sun, I'm blacking it out, so it's all black. And if I have something actually drawn, then we draw it. So do I have my end result here so that you can see where we're going with this? So my end result is it. So basically that's the tree that was rendered. Everything that you see here, it was rendered, and we're just superimposing our sun rays on it. Unfortunately, with this effect, it's very hard to see when it's a still image. So yeah, basically, if you move it around, you can actually really see it working. That's the effect that we're creating. So that's a 4-step effect, 4 steps. And we're just on step 1 right now. So I'm going to scroll back up. This, by the way, is all calls for the UI, I think. wonder if that's not something that can be optimized. Anyway, so yeah, we're just talking about the push constant. So that's a way to just send a little bit of data to your shader without doing a whole bunch of setup and nonsense like that. But like I was saying, right now we don't have structs implemented yet. That is something that is coming. So you just need to build a buffer, and I've just chosen to do it as a float array because I need some floats, and just put everything in there, even things that aren't floats. And then when we are doing our pass, which is in this case a compute shader, we are sending our push constant here. Now you can see that I'm actually treating my push constant as a byte array. So I'm doing conversion to a byte array. And obviously, yeah, every float is 4 bytes, so I'm multiplying my size by 4 to get my size in bytes, and that is what I'm pushing into towards Vulkan, so that Vulkan knows. I'm actually coming to that point, so like I said before, we can use these nice little draw begin labels to help us debug things and see those. Now we're getting to a compute step, and this is where it starts getting a little bit more technical, because we really need to start talking about how compute shaders work. And I don't really want to go into too much of the detail there, but let's, before we go through these few lines of code to figure out, okay, what's it doing here, let's have a look at the actual shader that does this. That might make a little bit more sense. So, I think none of these are the ones that we're looking for. We're looking for our make sundisk.gsl, DS, I can't even say that, GSL, no, GLSL, there we go, that's the one. When we look at our compute commands, so we start a new compute list, and the first thing that we do is we bind a pipeline. I'm just going to go quickly up, because this is in our initialization. I'll talk a little bit more about the initialization later, because there's a couple of really funky things that we need to do, because we could be running our rendering on a separate thread. But basically, our pipeline is being created here from a shader. Vulkan allows you to compile shaders. That's the little, program that tells it how to draw stuff. But then you can create a pipeline around that where you combine additional information. You combine the shader with a frame, or with a definition of a frame buffer, I should say, with, are we blending? Are we, all sorts of other things, which is actually more important with the, do we do any, we don't do any raster shaders here. That's more important with the raster shader. With the compute shader, it's not much for variation here. But you could use a shader in multiple different pipelines. That's really what I wanted to say. In this case, we always have just one pipeline for each shader. So obviously our pipeline is creating from a shader. Our shader here is loaded from a file. So Godot just loads our GLSL. This is a stock standard, plain vanilla GLSL file, unlike when you define shaders for materials, where you're only writing a bit of GLSL Godot code that is then parsed by Godot and inserted into the full shader logic that does all our lighting and drawing and God knows what. For this stuff, you're rewriting the full GLSL shader. This is exactly what we are sending to the GPU without any further modifications. I do believe that we have the ability to parse and include files, but that's I think about it. The rest is just what you see is what you get. Here you go. Thank you for coming. So we just load that. What is really cool is this is actually a string, and we have a helper method on our strings, get spearv, which encapsulates our shader code into a spearv object, which is then, when you call the shader create from spearv on our rendering device, RD, by the way, here is a variable. You can see it actually up here. We have just obtained our rendering device from our rendering server, so RD points to our rendering device. We're basically telling it, go and compile it. Compile it, get a pipeline, and we can use it. 7 compute shaders are definitely magic. And again, I'm going for a very complex example here because I just wanted to show you guys, just walk through it. So don't worry if you don't pick up everything that I'm talking about. Once we do that, I actually want to build one from scratch. And we're going to build a very simple one, but we're going to do something a little bit different in the way that the shaders are applied. So that's where it's going to be fun. Sorry. So back down here. Actually, let's go and have a look at a shader. This is a computer shader. So most of the people who work with Godot, especially if you have gone to the step of creating a shader, so not just using the standard material and set it up and use it for your objects, but instead you actually go down to let's write a shader ourselves, or the really cool thing in Godot is you can go to any material that you've defined and you click on the material, you say convert to shader material, and you can see the exact. Actually, it's a good thing. That's a bunch of new people here. So let's actually show that. A little quick side step. So if I go and add a new mesh instance into my scene, there we go. Don't really care what it is. Let's just make a box. There we go. Big box. Hello box. There's a box. And if for this box, I now create a material. So I'm going to go for a standard material here. And let's give it a texture. Do I have a nice texture here? Oh, let's go into assets. I'm pretty sure there's some textures I can use from here. Look at that. Oh, those are all UV unwrapped textures. Not really nice for what I want to do. Yeah, let's put a screenshot on the texture. It doesn't really matter. The point is that it does something. Let's say in a normal map. I need a normal map. I don't have one. What could be fun to do here? Let's give this a refract. Make it refract some light. So that means that we need to make it transparent. So let's go make it a bit transparent. Does that work? It doesn't really work with a box, doesn't it? Refraction with a box. Should I turn it into a circle then? This is probably going to make me lose my material if I do that. Well, it doesn't really matter. The point is, I just wanted to put a few things in there. Because what we can now do when we have a... so I could like to create a cloud GSS when in Godot's editor, make new shaders based on that. Instead of rendering these separately for meshes with regular Godot shapes. Not quite sure if I follow you fully, Martin. Hold on, there's more here. Is it possible to create a GLS on master shader that can be used to make shaders in editor? Like our shaders in Godot get... okay. That should have read your first message. Not with this, but that is the thing that I am working on next. So, and I actually wanted to start working on that last week, but I have been busy helping lots of people on board from new people who are interested in Godot because of all the Unity stuff. So I've been a bit preoccupied over the last week, but I'm hoping to really get into it this week. It'll probably take a little while for me to build. But yeah, so, well, we're actually almost at that point, because if I now do the drop down here and I say convert to shader material, then I get a material with a shader. And here I see all the code that that standard material has generated, because in the background, a standard material just creates a normal shader. And this is our shader code. However, and then we come to Paper Martin's point, this is a bit of code. Anybody who's ever written full GLSL shaders, look at the vertex shader. That's not a whole vertex shader. There's a whole lot of stuff that happens in a vertex shader. We're inserting a tiny bit of code into a larger shader that has all the standard inputs, all the standard logic for displaying an object on screen. The fragment shader has all the standard lighting information in there. We are just controlling like the heart of that in Godot, and we're inserting that into a large template shader that's built into Godot. Now the work that we're planning to do in the next couple of weeks is for users to be able to make their own version of that shader. And we're hoping to get to a point where you can even say, hey, I want to include all the standard bits so that I basically have the standard logic in Godot, but I want to do a few tweaks. And I want that to become my template that I use for all my materials in Godot. So that is something that we are working on. And we'll see how that goes. That's my my next thing that my next big thing that I want to be working on, unless there's something else that suddenly pops up and gets priority, I will be working on that, and hopefully with a couple of weeks we'll have something up and running. Hey, New Games, how you going? Sin, I don't know. I've only ever worked with GLSL in Godot. I don't know if we actually have the HLSL parts of SPIR-V embedded in Godot, whether we only compile in the GLSL compiler. Although that said, seeing that SPIR-V is included, I can't imagine that it wouldn't be difficult to add if we really want to do that. I do know, if I'm not mistaken, that the DirectX render device that Pedro is working on is all GLSL based, and that choice is made because all the internal code in Godot is GLSL. To also then have to maintain HLSL versions of those shaders, that would just be crazy. That would be for a small team as ours, that would not be a good usage of our time. So anyway, I just quickly wanted to show that that any material in Godot, you can actually go and you can convert it to a shader material. You can actually see the code that we generate, and as you can see, that code, even though it is in basis GLSL, it's nothing like an actual GLSL shader program. And again, this being then a compute shader, but even for a vertex shader or a fragment shader, the setup is basically the same. So, compute shaders. What's so special about compute shaders? So when we are talking about a normal raster pipeline and a normal raster shader, we are talking about rendering geometry. So we have a bunch of vertices that are joined together in through an index buffer to render triangles. That's the simplest description that you can give of a raster pipeline, of a renderer. And shader-wise, that means that we have a vertex shader that allows us to tell the GPU how a 3D vertex in space needs to be converted to a point on screen. Then all those points, we have 3 points for a triangle. We run 3 vertex shaders to figure out where those points are on screen, and all sorts of other properties that we need to know. And then the rasterizer is going to turn that into a triangle, and then for every pixel, I shouldn't call it pixel because especially if you use stuff like MSAA, it's a little bit more complex. But I like to keep it simple. For every pixel that ends up on screen, rerun the fragment shader. And the fragment shader then determines the color of that pixel based on lighting and all sorts of material properties and all sorts of other things, whatever you put in that shader. A compute shader is much simpler. Compute shader doesn't draw shapes. A compute shader simply takes a bunch of inputs, runs through a number of iterations, and outputs something. And you can use that for just about anything where you just need to crunch through a whole bunch of numbers, including going through every pixel in a texture and basically, doing some sort of processing on a texture buffer. Now, what is really cool about compute shaders is that they are optimized to process as much as they can in parallel. And if your shader is such that it can make use of it, you can even share information between those threads so that not every thread needs to do the same calculations over and over again to come to the same result. If that's an input that it needs to do, then do the rest of its processing. Now, in this case, I haven't gone back to that level of optimization. I've kept this process fairly straightforward because this was meant as an example for showing how to chain compute shaders together to get a nice end result. And I wanted to keep the actual shader logic as straightforward and easy to understand as possible. At the top, we just see the identification. This is a compute shader, and we are using GLSL version 450, which is based on, I guess, an OpenGL 4.5 format. I'm not sure. But basically, you can instruct the GPU to what level of instructions you are going to use so that you don't end up running OpenGL 4 code on an OpenGL 3 backend, which of course for Vulkan is, we're using GLSL. I'm not quite sure. I'm not quite sure if there's any point of putting something like this at an older version of OpenGL. I think it doesn't really matter. Anyway, that's always at the top. This is the more important one. Layout, local size, X, Y, and Z. So like I mentioned, compute shaders are attempting to run as much in parallel as possible, and it does that in groups. And I'm not using the correct names here. If I'm not mistaken, these are called waves or something like that. I always mix those terms up. Wonder who always comes up with the funky terms. But the idea here is that we're actually ending up, 8 times 8 times 1 is we're going to be running a chunk of 256 simultaneous threads churning through, an 8x8 piece of data. And what that 8x8 piece of data is, the compute shader really doesn't care. We are going to determine that in our shader code. All that we know here is that we're running chunks in 8x8 groups. And for some effects, that's really handy because you know what sort of bits of data that you're handling in one go, and you can, like I said, you can share data between those what they call is it instances? Yeah, no, invocations. So we get 256 invocations of this this shader that work as a group and that can communicate between each other and do work together and do things more optimal. This is a pretty good default to work with. Even if you are writing a shader that you don't really want to use that, it's still good to tell or to base your logic on a certain size. Now, in this case, we're running through an image. That's why we're using both the X and Y inputs. But if you're, for instance, going through a one-dimensional buffer, like say an array of positions for a particle shader, for instance, you might want to do, X might be 256, and then Y is 1, and Z is 1, and you build it up in that way. So with that defined, we now know that we're running in a block of 8x8. I'm going to quickly go back to GDScript, because with that, this bit of code starts making sense. So our effect size is actually our buffer size of our beautiful buffer here. I've added some logic here that I can actually do this at half size to save some processing power. Just again, as an example of how you might approach something like that. So we now want to break our image up into little bits, 8x8 bits that we're going to run our compute shaders in. So we simply need to divide by 8. Now you can see that we're doing a little -1 +1 trick. This is to make sure that we always we sort of upscale to the nearest 8. So let's say that we have an image which is 14 by 14 pixels. Then this will be 2 groups on the X and 2 groups on the Y, which also means that we actually end up with doing a little bit more work because our image is only 14 by 14. We're actually going to now be running 16 by 16. So we're going to have 2 pixels on the right and 2 pixels on the bottom for which there is no texture. And we'll see in a minute that we're actually capturing that. So we're calculating those X groups and Y groups. That's what we then call here. So basically, like I said, that 8x8 that we defined in the shader, every group is has 256 invocations in an 8x8 setup, and we're now executing that for this and this. So basically, we are executing enough groups to cover our whole texture. That's really what we're trying to do here. And luckily for us, when we go in here, I just wanted to quickly step to this line of code here. We can see that we have a global invocation ID. And this is a built-in variable that actually gives us which invocation within our whole texture, assuming that, that's what we're doing here. What pixel, what fragment, what element, whatever thingy that we're planning to do, that we're working here. There's also a GL local invocation ID, which gives us an XY within our local size. So, that could be 4,6. For every group that we execute, we'll have a 4,6 that is eventually being run. So what we're also seeing is that once we then, because we're just doing a conversion here from float to integer, we're also then making sure that, hey, if we are running this invocation for a pixel that actually doesn't exist in our texture, we simply return. So again, we're doing everything in these 8x8 groups. At the edges, we'll be handling a bunch of pixels that we don't have. We just exit the shader at that point in time. There's no way to size that exactly, because then we skip the whole parallel processing thing. So all right, so that's basically all that this matters. So this gives us our little tile size that we are working on which our invocation group works. We're still running the compute shader itself for every individual element in that 8x8 group. They just happen to all happen at the same time. And then that's run as many times as our group counts here. So now things are starting to get interesting. That's all set up, right? Here's our depth image. So we are here using a sampler 2D input. And a sampler 2D, that's basically a normal texture read. We are giving it an image here, but we are treating that image as a texture. For our GPU, there's a difference between an image and a texture. Texture has all sorts of additional abilities with a sampler. You can get nearest value. You can ramp it up. You can do mip mapping. You can do all that sort of jazz. While if you access the image, which we're going to do here in a minute, you're actually just accessing the pixels themselves in the image. So there's a little difference there. So when we are defining an input for us, the first thing that we need to do is we need to give it a set. And we have a limited number of sets available that we can put data in. And within those sets, we have a number of bindings where we can bind an input or an output on. Now, you can put everything in a single set. And to be very honest, I am not very sure in what scenarios you can't put everything in a single set. I'm just taking it safe here. I'm breaking them up because I only have a few inputs, but also because that allows me to reuse some of the uniforms in some of the other shader steps. Godot's a little bit weird there because you're actually creating the uniforms. Remember that we are creating the uniform sets here. We are actually creating them based on our shader. And that is because Godot in the background does a whole bunch of validation to make sure that everything is set up correctly for Vulkan. Vulkan is fairly precise in certain flags that you need to set and that sort of thing. But there's nothing magical about this uniform set that makes it a uniform set specifically for that shader. So any other shader that has the exact same definition, you could basically reuse that uniform. So there's a little bit of optimization there by sharing. It's neglectable. So if you just want to treat every shader separately, and you happen to use the def buffer in 3 shaders, and you create 3 different uniform sets for it, whoop-de-doo. It's all fine. One other thing which is important is that we actually have a uniform cache. If you would be creating the uniforms and the uniform sets every frame, that would be a lot of overhead. But Godot they got a little cache object called the uniform set cache. Oh, what's in the name? Where you basically say, I want this uniform, and that cache is going to say, already created that for you. Here you go. Don't need to go to the GPU and tell the GPU, need to have another uniform set. It's there for you. So we can use those. But yeah, we have defined here a layout. So we put that on set 0, binding 0, and then, well, it's a uniform. That is an input or an output for a shader. We type it as a sampler 2D. So we tell the GPU, this is a texture that we're going to be sampling from. And we give it a name, depth image. So in here, as I said before, we've created our uniform set over here. And we've created, I've got a little helper function here that creates a sampler uniform for me. This combines a sampler with the image uniform. So the depth image is a RID in Godot that points to the, or represents the depth image buffer. But we have to combine that with a sampler. So come back to samplers later. Don't want to go on that tangent right now. So I have just this little helper function here called getSamplerUniform. It's defined a little bit up in the code. So with that, we create our uniform set. So the uniform set could have multiple uniforms. So again, we could have, we could have multiple inputs here that we all put in set 0. So we have binding 0, binding 1, binding 2. That might be 3 different textures that we have as an input. You would combine that into a single uniform set to set those all through. So again, if you have a much more complex system of this, you might actually want to combine that and then create your uniform set just one time and just keep using that, not have it overhead to set multiple. When we then go down here to where we're doing our compute list, you can see that we are binding our depth uniform set to set number 0. So that's our compute list that groups all our commands for one compute pass together. Created that compute list here. We bind it to our shader, and then our next step is we bind one of our uniform sets. We've created the uniform set up top, and that's set 0. And that means that this set is now assigned to that input. The second line, we are in this case using an image 2D. And as a result, we have a little bit more complexity. There's a little bit more elements in this. The first thing is that obviously we have to bind it. So exactly the same thing, only this time I have a helper function called getImageUniform. And again, the code is a little bit more up above. It's just which types I set. In this case, I don't need a sampler. I just need the uniform RID. I create a uniform set from that, from our cache. So only create it once, not every frame. We just grab it every other frame. Create it once and then we keep grabbing it. And here we do the exact same thing. We bind that uniform set, that one, but in this case we bind it to binding 1. So that is set 1 over here. So that's setting our second input. Now when we look at our second input here, in this case it's an image 2D that allows us direct access to this image, to every pixel in that image. But we have a little bit more in there. In this case, the funny thing is when we are looking at our sampler, the information is in the sampler how we're getting data, and we're just getting that as a RGBA value, even if it's a one-channel texture, just like in normal shaders. But for our image, we actually need to define the type. So remember that at the beginning here, when we defined that buffer, we used the R16 unorm type. That means that we have a 16-bit floating point, unsigned normalized buffer. So every float in that buffer represents a color value between 0 and 1. That's the shorthand for it. R for the fact that we have only one channel, which is also the red channel. 16 bits, F, floating point. Note that in this case, we are not specifying that this is an unsigned normal. We don't need to know that. That information is kept in the image, plus that we can set whatever value we want to set, or we can read whatever value we can read. Obviously, that value, if you're reading from an image, that value is going to be constrained depending on what type of image it is. And when we're writing to it, the value will simply be clamped. So if I have a unorm buffer, which can only have a value between 0 and 1, and I write a 2 to it, the GPU is going to say, doesn't fit. I'm gonna cut it off at 1. I'm going to store a 1 in there. So it's going to automatically clamp that between 0 and 1. So we don't have to specify that extra information. Kind of nice. These two elements here are optional, but if you know that you're only going to write or read to an image, always include this because it allows the GPU to optimize stuff. So in this case, I am telling it restricted to writing. I'm only going to write to this image. I'm not going to read from this image. Very important. You can set or leave this out and create a uniform where you can both read and write from, to and from. But at that point in time, you have to be really careful, because if you read from a different pixel than you write to, and all your other invocations of the computer shader do that as well. And remember, these things all run in parallel. Funky things start happening because you do not control in what order that happens. So you can't guarantee that you're reading from the original image before it's modified and then writing everything out. You get a bundle of mess. So if you have to read from all over the place, let's say for a blur effect or something like that, you have to use like a ping pong approach. You have to read from one image and write to another image so that you're not overwriting things that you're still reading from and all that sort of stuff. But for, like my grayscale example that I had before, sure, I can read the pixel, turn it into grayscale, write the pixel. That invocation of the computer shader is the only invocation of the computer shader that touches that pixel. Happy, we'll do that. So with our two images, our input image and our output image defined, we are now defining our push constant here. Remember, already talked about push constant a little bit. That is that nice little buffer that we are filling up here. We are defining that here as well. Now, in this case, I am using, bigger constructs. So vac2, obviously 2 floats, vac2 render size, but I'm adding that here in 2 instructions. First, putting the first float in, my X, and then my second, my Y. That makes up our beautiful render size. Now, in this case, I'm making my life very easy because I'm just using floats. And in this case, I'm also using a few vac2s. Push constants have to be memory aligned. And that means that if I would do this, I'm in trouble, because the compiler will see a float here, and at that point in time, I can only insert another float until I hit the next barrier. In this case, it's expecting a barrier of 2, so it's actually, without us knowing, going to add another float here to fill up that space, because these guys need to always be on even numbers, addresses. So gets even worse if we do if we use a vac4 here. Put my fingers on the right place on the keyboard. Thank you. So we put a vac4 here. Those need to be, I really can't type tonight. Those need to be aligned by every 4 floats. So if our compiler sees this, it's now going to do this. Even though I don't type these, it's going to be aligned like that. Which obviously means that if I'm not expecting that, and I'm just putting my float in my buffer in Godot, and then I'm putting my, my test thing in there, my vac4, yeah, that ain't going to work. So the rules around this, once you figure it out, it's pretty straightforward. I can't explain it. I've been doing this for so long, it's just a natural instinct. But just think about that everything is just in blocks. If you use vac4, everything is in blocks of vac4s. If you have a matrix in there, It's obviously, you know, a block of, what is it, 4x4, 16 floats. Yeah, that needs to be on 16, you know, allocations, you know, blocks of 16s. So again, if you have a float and then you follow it up with a mat4, a projection matrix, it's going to put in 15 dummies. It's going to memory line it like that. So let's see. Yeah, let's go, Starwolf. How are you going? I mean, 2 hard problems in software development: cache invalidation, naming things, and off by 1 error as well. You can be off by 15 in this one, but yes. So yeah, we are defining all these things here. We are adding them all into our push constant there. We are getting them over here and Renderdoc. If we go into Renderdoc, we've got our command that renders this this thing selected. We can actually go to pipeline state. We can see that all our pipelines are disabled because this is a compute shader pipeline. And then over here, we can see that we have push constants. And if we click on that, we can see that Renderdoc is able to show us what information we sent here. So in this case, we see that our render size, so that's the resolution that we're rendering at, is 1152 by 648. We can see that our effect size is the same because I'm not using my half size option, else that would be half this size. We have a variable called sunpos. So here is one little problem. We do have access to the data in the shaders that actually store all the directional light information. That information is actually accessible, but we haven't exposed everything of that yet to the render effects thing, because that actually requires us to expose much more of the rendering pipeline. That's probably going to be part of the whole process of the custom shader templates, because at that point in time, we're going to have all sorts of include files that gives us all the structures of these things, including the structure that is filled with direct light data, so that you can actually access those in your compute shader if you bind the uniform, because they're all stored in uniform sets. So you have to then bind the uniform set. But for now, because we haven't done that part of the system yet, I'm just calculating it. So there's a point here, I think it's in my main script. Yeah, in process, I am actually copying the direction in which my directional light is shining. I'm copying that into my script. I've got a property there called sun location. We can see this. Where's my scroll bar? Why is my scroll bar not working? Because I'm not on the right scroll bar. Thank you very much. That was the resize bar. So over here we have where are you? Sun location. So we have that that variable declared here. Is that one that we are setting? Yeah, sun location. So that is being updated in here. So as my sun changes, that is also updated, which is really nice. And then where we're where we're calculating our constants. Oh yeah, sunpos. Actually, there's a calculation here. So I'm actually using. Do I want to go off this tangent right now? Why not? When we're coming into our callback, we get an object called render data. And render data allows us access to our render scene buffers and render scene data. Render data actually also has access to some other data, but again, that's all to do with the buffers that contain light data and stuff like that, which we don't expose yet because there's a whole bunch of stuff that we still need to do around that. But these two are very important container classes. Now we do cast them to our render device versions of them. There are class 3 versions of this for the compatibility renderer. However, those ones aren't fully implemented yet, which is one of the reasons why we haven't added this stuff into the compatibility renderer. But the same sort of thing applies. So our scene render buffers, if we click and go to the help of that, this gives us access to all the buffers that are in play. So it gives us access to the depth buffer, it gives us access to the color buffer, gives us access to motion vectors, gives us access to the blur buffers if they are created. So there's a whole bunch of, render buffers are effective. Our motion vector buffers are in there, Kyle. Yes, they are. As long as you've got that enabled, you can get them. I haven't actually played with those yet. You can actually see that here, the velocity layer and velocity texture. Note, by the way, we have entry points called layer and texture. In a normal application, they actually return the same thing because we only have one layer. These are specifically introduced for stereoscopic rendering, so VR stuff, because there every texture has two layers, a layer for the left eye and a layer for the right eye. When you call get velocity texture or when you call get depth texture, you get a texture that has both layers in them, and you can use them at the same time. If you call depth layer, you get just the layer for that eye. So you can get a texture ID for the left eye and a texture ID for the right eye, which is what we are doing in our code here. We're actually looping through every view. You can actually see that here. We have this nice little loop where we're looping through the number of views that we have. So 99% of the cases, get view count will return 1, and calling get color layer 0 and calling get color texture will return the exact same RID. They work the same. Stereoscopic, they're different. So be aware of that little change, which is why I tend to call the layer ones, because that's the safe one. If you do a loop through the view count, and you just get the images for layers and you build your effects on that, it'll work in a stereoscopic environment. And in this case, because we are processing a whole image, and we're not drawing inside of the image, doing one eye first and then the other eye next is just as fast as doing it all at the same time. It's the same amount of work. So there is no real overhead in doing this in a loop. Hey, see, how you going? Well, I haven't been streaming much lately because of busyness and stuff like that, but I plan to pick it up a bit more. But yeah, I'm glad to see you again. Excuse me. So yeah, there's a whole bunch of things in here. Now, these are all convenience methods. All the textures are actually named. So the base method is actually get texture, which takes a context and a name. And that's something that I need to start writing documentation for, so that, because right now you can only find those in the source code, or a little bit of trial and error, or looking at other people's examples. But there are a set of internal ones that you can access, and they're all by string names. So for those who aren't aware, string names are names that are resolved to an ID, and that ID is guaranteed to always be the same for the same name. And all through the application, that's stored. So just as much as, it's basically an enum, but with an extra step of processing it. So makes it easier. It's easier to read, easier to understand what's going on, and it's more extendable, because in our case, we can see that I'm scrolling the wrong way. We're creating our own. So I'm create a variable called texture, or a context, and a variable called texture. And if we go up, you can see that these are just constants. So our context is radial sky rays. Our texture is texture. Not very imaginative of me. And our pong texture is called pong texture. Also another very imaginative name. Now, the context is really important, because if there is something that changes that requires you to recreate the buffers, but it's something that Godot cannot automatically detect, you actually can tell it to clear your buffers by clearing your context. It will not touch anything else in the rendering pipeline. It'll just clear the things that you created. And we actually can see that in our code, because I've done that for when our half size changes. So where did I do that? Oh yeah, here I'm checking whether my effect size has changed. So I'm checking, hey, do I have a buffer? If so, I'm actually using the get texture format to get information about how this texture was created, and I can check if the size is the size that I want. If not, I'm simply calling a clear context, and that clears all the textures that I've created for my effect without touching anybody else's. And after that, I check again. Do I still have a texture? No, I just cleared it, so it's gone. Or Godot cleared it for me. so it's gone. At that point in time, I tell it, create my new textures. And now that I've created my textures, I can use them by, or I can get them by calling get texture slice. Now, why am I calling it slice here? And I'm calling it layer over here. Slice is an internal name that we were using, and layer is a name that we have used for ages. And they kind of, yeah, I think layer makes more sense in this case, but it's in a name, right? Yeah, that's the only one that I'm sort of going like, maybe I should call them both slice. I don't know. But yeah, I think in our way, layer makes sense because we're grabbing a layer. Sin, are they hashes? I think they're actually resolved to IDs, but I haven't never looked into the internal implementation of them. I just know that it is a system where we do that one time at startup. String name is then encapsulated, and the actual variable that we set is some sort of integer ID or pointer ID or something like that. I'm not quite sure, but it's guaranteed to be uniquely linked to the name that you set. So, yeah, it has the same function as a hash, but there's more overhead in looking it up. So it really is designed to be requested once and then used over and over again instead of re-looking up. While with hashes, you tend to more quickly try and reproduce the same hash to see if you got the same value. All right. So that's it for push constants. That's variables that we want to bring in, limited to 128 bytes. Memory aligned, so be careful with that. Use Renderdoc if you're not sure. If there is indeed a situation where things shift, you will see that here. You'll see that your numbers are on their own place. And you know that, oh, damn it, it's inserted some blank space there. It's memory aligned everything. And all of a sudden everything is, because of course in C it doesn't happen. And in here it doesn't happen either. In here, the what you put in is what it takes, even if it expects a couple of blank floats in there. So that's just something to be aware of. So yeah, use Renderdoc if you're not sure. But other than that, yeah, just be careful of that. So going to our actual code that we're doing here, this is really straightforward. An epsilon is just a little helper variable to deal with small rounding errors in floating points. We get our render size, which I don't believe we actually use in the shader anymore. We're purely using the effect size here. Ta-da! Very happy. So as we already discussed before, we're using the global invocation to figure out which pixel this invocation of the compute shader is supposed to do something with. And then the first thing that we do is we get our depth value. And for that, we need to calculate a UV. Now, here's an interesting difference between using a sampler. Remember, we defined that as a sampler 2D, which meant that we have to use a sampler, and direct access to an image. When we are using text-to-load, which is the function that we're retrieving it in the value for, that is the function with which we are retrieving the value, we need to use an UV that's normalized. So a value between 0 and 1, where 0, 0 is your top left corner and 1, 1 is your bottom right corner of the texture. Which is very important because when you're rendering, it's upside down. So trips a lot of people up, including me, all the time. So we're calculating a float, and we're doing that by taking our sun disk, which we are now casting back to a normal floating point value, and we're dividing that to our effect size. Now, one little thing that is interesting is that I'm obviously sending our render size here, but I can actually get that from the image itself. There are functions to retrieve the size of the texture or the size of the image. I actually don't know what is faster, whether it's faster to just tell the shader that, or whether it's faster to retrieve it. My gut feeling says that telling it is faster because you do that once. While if you, execute a function in your shader to get it from the image, it needs to do a fetch or something. Hold on. Hey, Patrick, how you going? Always good to say hi. No problem if you're only here for a few seconds or minutes or however long you have. Sin, yeah. Again, when we're looking at render effects at this point in time, it's pretty low level, so there is a lot more to look up. And for some things, you right now need to look at the source code if there isn't someone who has an example. But I do plan to update the documentation once this is everybody's happy with what I've built and we're merging this. Then it's time to write the documentation. I just don't want to write the documentation when things might still change. But also, I think that me included and other people will start building things on top of this to make it easier to use for other people. And we're burning through time here, so I hope that I get to my plan around there. But I do want to run through this explanation of this, because this is what people will start downloading and pulling apart. So it's good to have a commentary to it. I also need to see if I can find the time to actually put some timestamps into the description so people can use this as a bit of a reference of how this all works. Hey, Jackie, Ansir, how are you going? Yeah, it is almost 10 at night, so yeah, it's getting a bit late. But I'll probably continue for another hour or so. I don't want to make it too late. I've had a couple of days that I haven't gone to bed until 3-4 a.m. But c'est la vie. That's what you sometimes get. Ooh, meetings. Meetings are always interesting. It's actually a good point. I need to make sure that I wake up in time tomorrow morning because I got a meeting in the morning. Alrighty. So when we're using texture load, you have to make sure that we normalize our UV coordinates with, again, 0.0 being the top of the screen, 1,1 being the right bottom of the screen. I hope that my image isn't actually... I suddenly realized that maybe the image is lit on my screen. I don't know. So yeah, turn it around if it is. So that's why we're doing this. We're dividing the UV by the size, and we're getting our depth. And all we're doing here is we're checking our... Oh yeah, and obviously the depth is a single color channel buffer. Texture load always gives a VAC4, so we are taking the R channel, the red channel, and that gives our depth value. Now our depth is what's the right word for this? It's perspective encoded because it's divided by W in the calculation. So it's if we actually want to know the exact position, exact depth, we need to do some math. But in this case, all we're interested in is there anything in front of the background? We're only caring about the background. So the background is always 1, right? So 0 is near, 1 is far or anything after far. So if it's 1, that means that we don't have anything rendered there. Anything smaller than 1 means that something was rendered there that wrote to the depth buffer, and so our tree. So what we're simply doing here is if the depth is smaller than 1 and something is obscuring our sun, we are writing zeros to our image. And as a result, that is why we have all this nicely black. So this is everywhere where it's black here is where our depth value was smaller than 1. Hey George, how you going? Greetings from Sydney. Everybody there in Europe must be waking up by now. I'm not sure what time it is over there. Okay, so the next step that we're going to do is we're actually going to calculate where our sun is in our image. So we are taking our sun's input, which we are then adjusting. So when we take our vector and we, oh, that's what something that we were talking about a minute ago, wasn't it? So I skipped over that when I was suddenly talking about the fact that we are getting our render buffers and we're getting our scene data. So our render buffers gives us access to all the textures that we're rendering with. Our scene data gives us action to some scene state. Now, I went directly to this one as in any methods because we actually have a lot of methods, or a couple of methods defined on our base class, because really every rendering engine needs to implement this. So the things that we can get is our camera projection, our camera transform. We can get our uniform buffer. That takes a lot more explanation and is currently not usable unless you copy the internal structure from the rendering engine, but that will become usable. Basically, it gives you access to everything already loaded into the GPU. So you don't actually have to, because right now I believe that no, I'm just using it in GDScript in this case. But if I want to use the matrices in my compute shaders or in my raster shaders, I can use that uniform buffer and all the data will be there because it's already loaded to the GPU. But that is that's still some documentation that I need to write. Now, obviously, we have our view count here. We also have our view count in our buffers object. You'll see that one pop up everywhere. Again, gives us the number of layers, the numbers of views. It will always be 1 for normal situations. It will be 2 for XR. Might even be 4 once we support Vario, which I'm working on. And then we have these two, which are again for stereo. So I'm not going to go into them too far today, but in stereo, every camera actually has 2 projections, one for the left eye, one for the right eye, and the offset of the eyes are encoded in the projection matrix. So our camera transform in XR will actually be a transform that is between and slightly behind the eyes. It's not between the eyes, it's offset to make sure that the camera projection that we have here becomes a view frustum that encapsulates the individual eye views. And we do that because that now becomes a view frustum that we can call on, so that we only have to call once. We don't have to call individual for each eye. That's, for further discussion of that is for another day, because that's really interesting if you want to know how XR works internally. For our purposes, we need to know that when you are working on a non-VR game, a normal one view game, then get cam projection and get view projection will return the exact same value for obviously view 0, because you only have view 0, and get view eye offset will be a 0 vector. In XR, that will either give you the projection for your left eye or your right eye. That will give you a projection that you really can't use in shaders. That's purely at this point for culling. So that's what we have access to right now. There is a lot more data that is being stored in the scene data object that we're not yet exposing, because right now you can't use them anyway. We need other parts of the system to be finished. But these are by far the most important for almost every effect. You want to have access to your projection matrix. You want to have access to your camera position. Lots of effects need that information in order to do what they need to do. And we actually need them in a minute as well. Because in here, where are we? I am actually getting our projection for our view. I'm also getting our eye offset, even though for our effect right now we don't really need it, but I'm just being careful. And I'm getting my view matrix, which is actually the inverse of our camera transform, because we are now looking from the reference of the camera, while the camera transform is in world space. So it's the inverse that we need. So we're grabbing those, and then we're using those to project our sun direction onto the screen, so that we have the location of where the center of our sun is in our image. However, those are normalized values. So when we have a image like this, let's see if I can make that a bit bigger. So if you have an image like this, that's minus 1, minus 1, 1. Down here is 1, minus 1. 0, 0 is at the center of the screen. So our sun center that we calculated is somewhere over here, which we should be seeing, because in our thing here, we have our sun position. So slightly to the left of center, slightly up. That's pretty far up. Yeah, because it's about halfway up. So this is about a quarter. So yeah, that sounds about right. So a little bit to the left from center, halfway up from center. It sounds about right. So that's the coordinate that we calculate. That's what we're sending through. However, we want that coordinate in texture space. Hence the calculation of times 5 plus 5. So that means that now instead of having a value from minus 1, minus 1 to 1, 1, we now get a value from 0, 0 to 1, 1. Note the minus in front of the y. We are flipping the y because in 2D world, 0 is up, 1 is down, and in 3D world, 1's up and 0, well, minus 1 is down. So think about that one. Get it wrong all the time. Jackie, if I did not, lunch is not too bad. If it's not put in the description, is it not? Then I must have just been tired. Yeah, it's over here. If a single view is rendered, this returns the camera projection. If more than one view is rendered, this will return the projection for the given view, including the eye offset. So the description is actually in view projection. We're not doubling up on the cam projection, or is it? No, we are. If more than one view is rendered, this will return a combined projection. So yeah, could maybe have a little bit more, but yeah. I actually wrote an internal document once for how that actually is all put together. Should really turn that into a page on the documentation. Anyway, so yeah, be aware, we flip the y, and then we multiply by half plus half. It's a little trick to normalize it. And then we multiply it by our size. So now we don't just get a normalized location, we actually get the exact pixel that that our sun position is in. And what we do next is we calculate the distance or the length. Yeah, distance is actually a better description here, between the pixel that we're currently handling in our computer shader and that sun position. So if we're currently handling that pixel there, that distance will be 0. If we are doing that pixel over there, the distance will be, I think this thing was about 100 or 150. It should be right here. Oh, 250. So that would be, it's a radius of 250. So that would actually be a distance of 250 when we're actually on that edge here. If we're somewhere over here, we probably have a value of 400 or 500 or something like that. So we're calculating the distance of the pixel that we're currently processing to the center of our sun. That's what we're doing here. And then we're doing this little funky bit of math where we are subtracting the distance from our sun size. So remember, our sun size is 250. That means if we're exactly on the center, 250 minus 0, 250. If we're exactly on the edge, 250 minus 250, we're at 0. If we're beyond the edge, we get a negative value. So any point over here, we're now a negative. At any point between here and here, we go from 250 at the center to 0 at the edge of the sun. That's that bit. We are now dividing that by fade size, which is 5. So that means that over here, we are at 0. 0 divided by 5 is still 0. A little bit in here, we're at, say, 2. 2 divided by 0 is, what is 2 divided by 40? 0.4. If we're at 5, we get exactly 1. If we're somewhere over here, I'll be at 10. Once we're here at the center, 250 divided by 5 is 50. And we now clamp that to between 0 and 1. So our ending value here, our sun value, is 0 over here. The further we get out of here, we stay 0. But as we go in, that first 5 pixels, and you can hardly see it here, we really need to zoom in for that because it's only 5 pixels. We can see that we're slowly increasing from 0 to 1. And once we hit 1, we stay on 1 and we go out. So we can see that we get a nice little transition of 5 pixels going from 0 to 1. That's all we're doing there. And obviously, once we calculate that, we write that out. So, forgot that, by the way. When you're using an image 2D, you have 2 functions. If you're reading, image load. If you're saving or updating, image store. So what we're saying here is, in this image, at this UV, store this value. We're changing the value of that pixel. That is basically a smooth step. Yes, Sim, that is a smooth step. In GLSL, it's clamped. But it's the exact same function. Still hold me. Yeah, lines. It could be. I always mix them up, but actually, let's read up because I think I'm missing a couple of things. We have a lot of internal rendering documents pastes that are all over the place. Yep, they are. It would be nice if we collect them all in a public shared. Well, I actually think they should be in the manuals. I think we should have a section in the manual for the people who want to know what's happening behind the scenes, where we then explain some of these internal processes. And if we ever have time, we'll get to it. Time's the big factor here, because the other thing, of course, is once we write something like that, we also have to maintain it, and we tend to forget that. These things tend to become stale pretty quickly, so that is another part of it. I wonder why it's... Oh yeah, because I was doing all the dummy things. This is probably really dumb. You know what? Save. Should not be... All right. So that's our first step. So I really went through the whole shader here, and I hope that everybody followed along, even though we jumped around a little bit. I'm terrible for keeping everything on track in that way, but there was a whole bunch of ground to cover. But that's our first step. So our first step is our render sundisk. All we're doing there, read from the depth buffer. If there's something there, make it black. If there isn't something there, calculate the distance from the center of our sun to where we are, and then depending on that, determining a value between 0 and 5 so that we have a little up ramp on the edge of our sun. That's step 1 of our process. What we can see is that when we're doing a compute list end, we are specifying a barrier mask compute. And what that means is we're basically telling Vulkan that, hey, we just executed a compute shader. You need to wait with further compute steps until this is finished. You can do other stuff. You can go and do other sort of rendering. But my next step is going to be another compute shader. So wait until I'm finished before you do more compute shaders. Because else I'm going to have a problem because I won't be finished and you're going to work on the assumption that I am. Hence the barrier here. We can also see that we have a draw end label that matches up with the draw begin label here. And that means that everything that we've done in here gets grouped together into that label, which again is purely for debugging, only included in a debug build. Runtime build will filter it out, but it allows us in Renderdoc to nicely see that grouped. One little footnote, by the way, not on mobile. Hate that. I do not get why nobody is implementing this on mobile. On mobile, we're not getting this information. It is so handy to have. Makes debugging your render pipeline so easy. And it's just ignored on mobile. what do you do? So our next step is our radial blur step. So again, at the beginning here, we are saying that we have 4 steps, and our next step is a radial blur. Now with the radial blur, this one's actually quite expensive. I have directly copied the code that Harry used in his example. You can probably optimize that quite a bit, but you know, this was just an example just to show how to do things. So we're gonna keep it simple and readable. Right now is a little bit more important than performance. So our step 2 is doing our radial blur, and we see an exact replication of what we did in step 1. However, in this case, we are, actually, let's go to the shader first so that we can go and walk through this side by side. So again, same thing, compute version 450, that's always what you have on top. I'm still using an 8x8 compute group, wave group. However, now both my input image and my output image are images. I'm no longer using samplers. I am reading directly from these things. So in this case, I need to define them properly. I need to do my typing, R16F. I have them divided in 2 sets, so set 0 and set 1. And again, like I said before, we could put them both in set 0 and then choose binding 0 and binding 1. But in this case, I'm just keeping it simple. And in this case, it will also not really matter performance-wise. However, I'm reading from the first one, and I'm writing to the second one. Hence, this one's called input image. That one's called output image. Very simple, straightforward. Then here, we can see that our input image is the texture image that in our step 1, we output to. Where? Texture image. Boom. Oh, this is another nice little thing. If we go back to Renderdoc, whenever we use our buffer cache, so our scene buffer object, we can see that they're actually named. So we can see here is actually our context name. So render buffers is the context. So if instead of using get depth layer, we wanted to use get texture slice, then as context we would be using render buffers, and as the texture name we would be using depth. And you can see that on our output, same thing. So our context, radial sky rays, and then our name, texture. So it's nice and handy. We can actually recognize our buffers. Comes in quite handy. If you use the same effect for multiple viewports, you get a buffer for every viewport. We don't have a, we don't have an ID for the individual viewport, so they're going to be called the same on each viewport. That's a bit of a shame. That's something that we're still looking into improving at some point in time, but yeah, it's a minor inconvenience. No, there currently isn't really a guide of using Renderdoc with Godot, but you start Renderdoc, you go to launch application, you point it to Godot, you point it to the path of your project, and you press launch. And then you can press F12 to do a snapshot. And the rest is how to use Renderdoc. But that's where you start. So yeah, pretty simple. That's how we made this capture. So yeah, I love Renderdoc. It's so easy. That's basically what I'm trying to say. It's not a difficult program to use. The difficulty lies in knowing how the render process works. Although, again, the fact that we've named almost everything, and we've been a little bit better with this in the 3D renderer than in the 2D render, which is why at the bottom we see all these draw index 6s. That's all 2D stuff. On the 3D renderer side, we've done a pretty decent job with grouping it all all together. Okay. Anyway, back to our shader. So over here. So we're defining a texture set for our first texture, and then we are doing one for our output. So remember, we created 2 copies of our texture. because we're going to be swapping back and forward to that. So our first step wrote into texture. We are now reading from texture, and we are now writing into our Pong texture. We again want the center of our sun, but in this case, I'm actually already applying the calculation. In hindsight, I should have moved that a bit up and just made that the input of our first step, so I didn't have to put the calculation there. But it is what it is. So here we also have a push constant with a little bit different data in there. I have no idea why I'm mixing spaces and tabs. I think that is because for some reason VS Code always defaults to spaces, and I keep forgetting to change my settings because I want the default to tabs. But yeah. Anyway, I'll fix that up at some point. I'll pretty it up. So we're getting the size of our texture. In this case, we don't need the render size and effect size. We're just working on our effect size, so we only need it once. We want the center of our sun. Yeah, that's the center of the sun. So not the center of the image, the center of the sun. So that location over there. All right. We want to, so for radial blur, we are taking a number of samples to create our blur effect. So we're setting our number of samples. Those are all controlled, by the way, by properties over here. So we can see that we have our radial blur samples here, which is set to 32. And we'll once we actually start using this, we'll see how nice that comes back. Where were we? Step 1, step 2. We have our effect amount, which, we have our radius of our blur. So that defines how far out we stretch our blur in this case. We have an effect amount, how strong our blur is. And again, those are all values that we can play around with if we want. But those are all our inputs. And we can see again that we are setting them up. But because now we don't nicely end up on a set of 4, we also add an extra float in here. Now, if I don't define this, it will be added anyway. I define it because that way I can count and see if everything is still memory aligned. And it's just peace of mind that I know that I've verified that everything is there. And then someone else who might want to play around with this and add something more knows that, yeah, I can't just put a vec3 behind this. I have to, first do a float. So I can add another float in here. I can reuse that reserve one. But if I need another vec4 or vec2 or whatever, it needs to come after. Did my cam crash? That sucks. Okay, let's see if just resetting it works. This is going to be funky. I need a new, oh, that's my mic. That's not the one. Okay, right now. Deactivate, activate. Yay, it's working again. Thanks for that. I need a new little cam link thingy. I'm using a cheapo Chinese cam link knockoff. And when it gets hot, it stops working. I've actually ordered a new camera, so it should be coming in later in the week. And that should solve that problem, I hope. Anyway, thanks for noticing that, because I wouldn't have noticed it. That's the other thing that I'm still saving up for. I want a wider screen so that I can, or maybe a second screen, I'm not sure yet. But then I can have my my OBS on a separate part and actually keep an eye on things. Right now, as you guys saw, it's hidden behind my other windows. As for our shader itself, well, before we go through the shader, actually, let's quickly have a look here. So this part is an exact copy of what we were doing before. Where we're just starting a new compute process. We're binding it, this time to our radial blur shader. Exactly the same code upstairs to create the pipeline in the shader, just using a different shader file. We're binding our input, we're binding our output, we are pushing in our push constant. We are reusing the same number of groups because that hasn't changed. Our sizing and our invocation size still all the same, so perfect. And then we're executing, and again we have a compute barrier here because we want to finish this before we go on to the next step. Yeah, it's I used to have two screens because I used to be on a laptop, so I had a laptop and then my second screen. But I bought a desktop a couple of months ago because I just needed something a little bit more modern and a little bit more space, and specifically a couple more USB ports. If you do lots of VR work, you really start figuring out very quickly that a laptop does not have enough USB ports. And yeah, you can get little USB, like I've got one over there, one of those blocks with, not the same. You run out of bandwidth very quickly. So this thing has got some extra USB card stuffies in there that I got lots of bandwidth for USB. Kind of important. So yeah, I wanted to have a proper, a little bit more fleshed out desktop, but as a result, I only have my screen. I haven't gone around to buying the second one. I will in the end, but you know. Yeah, Stefan, I know I have been in scenarios where I've had much more than two screens, especially in my previous line of work. I don't know. It's one of those things where if you have the real estate, you start using it up, and before you know it, it's full and you want more space. But I can work pretty well with two decently sized monitors. One monitor, yeah, there are moments that I notice that it's a hindrance to productivity. I really wish that I had a second one. So it's on my wish list. Maybe I'll get it for Christmas. Proper USB block dock. Yeah. Yeah, you don't want to know how many I've got floating around here. Yeah, I'm always running out of USB ports. Yeah, especially when you're doing lighthouse stuff. Every where is it? Every one of these has a dongle. Takes up one USB. So I only have two at the moment because I'm just playing around with them. Thanks HTC, by the way, for giving me those. But yeah, if you want to do full body tracking, you got 5 of those. So, well, that's not even full body tracking. So on full body tracking, I think you need 7. So yeah, that's 7 USB ports sending out quite a little bit of data around. And of course, I don't have my camera for streaming taking up USB bandwidth, and yeah, it adds up. There's more things in there. So yeah, I wanted to have a little bit more powerful machine. So yeah, other than that, there's not much to say about this. It's actually for the next couple of steps as well. It's just repeating the same over and over again. It's the code in here that is important. And before we go through that last bit of code, we're actually going to have a look in Renderdoc with what we're actually doing here. So again, now here, this is one thing that I find, I'm not sure if this is a bug in Renderdoc or just a consequence of compute shaders. But even though this is our input, it's on the output tab. But yeah, here's our input image. And here's our output image. So we're going to go from this to that. So here we're seeing that our little sun is sort of blurred out by making it bigger and bigger and bigger and sort of overlaying each layer on top of each other. That's basically what we end up doing here. For MB, that's kind of what I'm thinking about as well. There's a monitor company here in Australia that is regularly doing sales, and they have these ultra wide monitors. And while on one side I'm a little bit scared of those because obviously that counts as a single monitor in your operating system. So if you're running things full screen, or if you're capturing your screen like we're doing with, well, in this case, right now I'm running OBS locally, but normally I'm using my Elgato to capture. That obviously becomes an issue if you have a widescreen TV. So that's the part where I'm still tossing and turning whether I really want to have a wide screen, or whether I want to go with 2 screens, so that I have one monitor on which I'm doing the thing that I'm recording, and then another monitor in which I have my OBS running and my I can see what the chat is doing and all that sort of thing. So right now I've got the chat running on a laptop, but I still have OBS running locally. I used, again, like I said, I used to go for my Elgato, but right now I have got that all disconnected because I'm having weird issues with my internet, and I found out that for some reason things are clashing, and I'm not sure if that's my router that's being weird, or whether it's on something on my ISP that suddenly says, hey, there's 2 machines going over this, we're going to throttle you. This has been really weird. It's been pretty stable. They did send me some messages that they're working on some things, that they were having some network issues. So I don't know. RW stands for read write. Yeah, could be. Could be because it's, again, like I said, it's a compute shader, so maybe it's not taking those hints up because they're internal. So potentially on when it's doing its what's the word? Its introspection on the shaders, it might just say, you know, here's an image 2D uniform, and it doesn't actually classify it as an input or an output. It just, you know, compute shader uniform, and it's only inside that it's defined. And in the end, I don't think it's a problem. You know, you just have to realize that sometimes your inputs are on the output tab. You learn that very quickly, and that's it. Okay, so all we're doing here is, obviously our start is pretty much the same as our auto shader. We're getting the size. We're getting our global invocation ID, which means, right, which pixel on our texture is this invocation of our compute shader handling. If that is outside of bounds, because, you know, we're doing everything in 8x8 blocks, like I said before, you know, our texture size might not be exact divisions of 8, so we might get a pixel that's actually outside of our image. So in that case, we return, and that's the end of our compute shader. And then we do our actual blur logic. So I have a variable called blur. That's actually our output variable. And every time that we do a sample, we're adding in that. We're also using a variable samples that I'm taking from our input. Now, that should already be floored. I'm being overly cautious here. This is actually, on the Godot side, that is an integer, comes from here. Yep, that's the samples one, so that's defined as an integer. So that should be a nice round number. But I'm being paranoid, just in case someone starts playing around with this and suddenly says that they want, 16.5 samples. I don't want it to break the logic, so I floor it, make sure it's nicely round 16. Thank you for coming. Then we're again doing a distance calculation by taking our current pixel that we're dealing with and subtracting the center of our sun. So again, this is a value that's 0,0 at the center, and then, you know, it slowly becomes a bigger number the further we go out. It doesn't really matter that, you know, obviously if we go in the other direction, they become negative numbers. Doesn't matter at this point in time, because all that we're doing is we're grabbing the length. We're storing a dist here because later on we're using that to offset things. So that's why we're doing that in 2 steps. But we're really at this point in time interested in the length. We are dividing that by our radius. So that's our blur radius, the amount by which we're blurring. And that normalizes that value and clamp it between 0 and 1, and we get a value that allows us to you know, sort of like compress and extend the image a little bit. Then we loop through the samples. We're getting we're calculating a scale based on our effect. Whoops, go away. Right. On where we are. So this is a value that as we go for samples, we start at 0 and we slowly go to 1, and then that ratio that we calculated here. So basically, this stretches the vector that we're applying, because that's the last thing that we're actually doing, is that we're using that distance that we calculated here, that we scale up by that scale that we just calculated, and we're adding that to the center. So this UV, this read UV that we right now get, is basically, if we look at the image here, then at a certain interval over 30, let's say that we're over here, we're going to stretch over that vector to that point that we are. We're going to take 32 samples, and how far the distance in between of those 32 samples are, that vector is basically stretched or scaled back depending on those values, giving that look that we're sort of slowly, expanding the image in several layers, and basically in 32 layers. So all we're doing right now is then with that UV, we're loading from our source image. So that's one of the reasons why we're not writing this back into the same image. We need two images, so that we can keep reading from the original image without that image distorting and not even knowing in what order things happen. It goes really bad if we do that. But no, we're reading all those 32 samples. So that's where this process is slow. For every pixel, we're reading 32 samples. But we're reading those and we're adding those into blurred. So if every sample hits a part in our sun, and our sun is always then 1, that would give us a value of 32. We have 32 samples, 32 divided by 32, we get the value 1, we write it out. If we're only hitting the sun in some of these samples, or we're on the border of the sun, then obviously slowly that value gets lower. And that gives us this nice, blurred out, radial blurred out effect. And you can sort of recognize, our image sort of overlaid on top of each other multiple times. So this arch here and an arch here and an arch here, it's all copies of that inner arch over here. And obviously here we have a much thicker, ray coming out, because that whole part here is red. So it's very likely that every sample we take is inside of our sun, and we blur it out. So also then obviously the more our sun is obscured, the less of a blur effect that we're getting. And again, this, like I said, we are taking it really simple here. This is the slowest approach of a radial blur, because we're just taking 32 samples for every pixel. Ways that this can be optimized is, for instance, that instead of doing this 32 times, we're doing this just once, but we're taking our previous result. And then after 32 frames, let's say that the camera doesn't move, because that's the tricky one if you do that optimization. After 32 frames, we would have this image, because every image sort of, we take the previous result, we sort of blow it up and then overlay that on a current result. Obviously, add a reprojection there, for which you need your motion vectors, and you can actually make that work with a moving camera. That would make this shader a whole lot more complex, but it also means that it has a lot less work to do, and it would be 32 times, well, not 30, it would be 16 times faster than this implementation. So just I think to sketch that, on purpose, I've kept this simple. I shouldn't really say I've kept this simple, because I basically copied this off of Harry's work, but I didn't spend any time optimizing it, because I wanted to keep it simple. I wanted to show the technique, how you put these things together, and not overcomplicate it by that sort of thing. But that would be a nice exercise for someone. Take this and instead of doing it like this, is keep a copy of the image around from the last frame and just overlay that onto your current frame. So You take that from your current frame, you also have it from your last frame, and what you simply do with your last frame, you make it slightly larger around the center point, and you overlay or you add it into this image, and that becomes your new image. And then obviously you want to keep one that isn't, no, that would still be blurred. So you would keep that, and that comes into the next time, blow it up, overlay it on your new image. Boom, that now has 3 things. Add in a reprojection, and you got this fast, basically. Someone wants to pick that up, go for it. It will be a fun little thing to do. So that's our radial blur. So step number 3, because the problem that we now have with our radial blur is that we have this really choppy look as those 32 samples have some spacing between them. And with 32, it sort of gets okay. But for instance, if we're going to do 16 samples, you really see that slicing look as every slice of the image is overlaid. What would faster versions of Radial? Yeah, so that's basically what I just explained. Is use reprojection, use your the last rendered frame, and it creates a little bit of startup time. But what's 32 frames at your startup, right? It's nothing. And that's where a lot of games will basically black out the screen for the first 32 frames while it actually renders the full frame in the background, just to create this this buffer. Okay. It's easy to do when the path is like that in Godot. I'm not completely sure what you mean by your last post for me. Anyway, so we just did the radial blur. Now we should be able to go a lot faster through these last 2 steps because it's basically we've covered everything. Now we're just reiterating. And like I said, because we got that little bit of choppy look here, we are now going to apply a Gaussian blur. And the problem that we have with the Gaussian blur is that to do it properly is fairly expensive. If you think that 32 samples is expensive, the Gaussian blur, you actually have to sample all around the blur, and that can be expensive. Now, there's lots of ways to improve that. And inside of Godot, you'll find actually a couple of versions, especially if you look at the depth of field function. There's various blur implementations in there, from taking a number of random samples around a pixel to doing certain shapes. But here in this case, we're doing a very classic Gaussian blur implementation in 2 passes. We're basically first applying our Gaussian blur horizontally, and then we are applying our Gaussian blur vertically. Still not the fastest effect in the world. And this is one actually where you could start using the grouping logic in our compute shader to really optimize this. But again, for our purposes in this project, I just kept it simple. But it's really an interesting step to see, hey, is that something that you can, swap out for something more performant? Yeah, so for me, we are actually separating out the Gaussian. We're doing it in 2 steps. So in this case, we only have one shader. We have our Gaussian blur shader over here, and we'll go through it in a minute. But we're now applying it twice. So we're at step 2, radial blur. We just finished that. So now we're going to do step 3. Now notice that above here, I swapped around our texture and our Pong texture images. They're exactly the same images, they're just grids. We can freely swap them around. Just makes it a little bit more easy to read. So all of a sudden, that is now our texture, and that is now our Pong texture. We don't care about that anymore. That result is old. We can throw it away. So that is basically now our source, our input, and that is going to be our output. We're only swapping the widths, nothing changes on the name. So we're going to see in a minute that even though I'm now saying, hey, my input is my texture and my output is my Pong, we're going to see actually in the shader that is the other way around. I could also just not have done this and instead just flip these around and make my Pong the input and my texture the output. Same old, same old. It's personal preference. I like the swap thing to sort of always say texture is my input, Pong is my output, even though I flip them around, because it makes it easier to move things around or insert another pass or things like that. But it's same old, same old. You can do it either way. Because in this shader as well, oh no, it's at the top. We can see that our top is again completely the same. We have our computer at the top. We have our definition of how we want our wave groups to work, and we have our input image and our output image. We again have a push constant, but our push constant in this case is just two inputs. One is our image size and one is our blur size, in which we also encode our direction. So for the first pass, we're going to put an X value in, no Y value. And for the second pass, we're going to put a Y value in and no X value. Then we have a standard table of Gaussian coefficients. We're doing a 16 left, 16 right blur. Can't remember which example code from someone I based this on. And then we do the blur itself. The blur is really simple. Again, we get our global invocation ID. Which pixel are we handling? If we're outside our border, don't do anything. We get our blurred value. I'm just copying our constant into a float value so that I know that I can use it. I am looping through the number of samples that I want to do, so we can see that we have 16 coefficients left and right, which means that we have 2 times 16 plus 1, our center point. So 16 that way, 16 that one plus the center one is in total 33 samples. And again, we could have limited it and only done 16 samples or something like that. This is probably overkill. And all we're doing here is we are taking samples along that line, and then we're multiplying it with that coefficient. Now, the cool thing about this coefficient table is that if you add all these numbers together, you get to 1. So our coefficients don't just make the pixels at the center more valuable, while at the edges we're only including them a little bit. We're also making sure that if we're doing this multiplication with the value that we're reading and adding up to our blurred value, our blurred value will be a value between 0 and 1. It will be bigger, won't be less than 0, and also impossible. It'll be nicely a value between 0 and 1. If all the pixels that we read are all fully set, we will get we'll write 1 out. So with that blur calculated, we're outputting that blur. So in our code here, we're setting our input, setting our output, or we're defining our output sets. And again, like I said all the way in the beginning, I could just be reusing a bunch of the earlier uniforms. I chose for clarity not to do that. For clarity, I'm creating them each time using our cache, so they're, if we already have them, we reuse them, so it's not really that much of a problem. But I could end up just reusing a bunch of these, even though they're defined on different shaders. They're all the same type. They're pretty interchangeable when they have the exact same definition. That's also one of the reasons for using different sets instead of using different bindings. If they're all binding 0, you can you can reuse them through all the shaders. We do our push constant. So here we can say that we've got our effect size, and then our Gaussian blur size. We are only putting in the X component. That creates a horizontal blur. We leave the Y component alone. We create a draw label, horizontal, and then again the same set of instructions we've seen time and time again. Create a new compute list, set the right pipeline, set our input and output, set our push constant, and go and run our computer shader. So in Renderdoc, we can see that we have our horizontal and vertical one. So right now we have done this. So remember again that we now have flipped them around. No, it actually shows them in the right order, which is nice. But we can actually see our input image is our Pong texture. So that is the image, exactly the same one as here. So that's the same guy. But then our output image is now our texture. And we can see that that's already quite more blurry. So that's just on the horizontal blur. See that happening. Then when we scroll down, what we're now seeing is that we're going to reuse a whole bunch of things. We're going to update our push constant. We're just going to create a new one. I should have just called clear. I'm not sure why I'm creating a new one here. Set the effects again. And then this time I'm putting the X to 0. And I'm putting the Y to our blur size. So now we're doing a vertical blur. Apply vertical blur as things. And here we can simply see that I'm now putting the Pong texture as input. And the texture is output. In this case, I'm not swapping them around. I probably should have for consistency. I'm not that consistent. Probably was tired. I should have put a swap in between here and then keep that in the same order. That would have communicated more that I'm going for that approach. But again, it doesn't matter. You can flip them around. It's right. And we execute that, and that is our vertical blur. So on our vertical blur, we're seeing that we're now going from this, which has only got the vertical blur in there, or the horizontal blur in there, to an image that combines the horizontal blur and the vertical blur, and we have a really nice blur. That's starting to look really, really smooth and nice and cool. So, sweet. And the last thing that we're going to do is we're now going to overlay this onto our original image. And there's a bunch of ways that you can approach this. You could do a raster shader with a additive pipeline, but because I wanted to multiply this with the source color, in this case I decided to go for another compute pass. However, when we look at our overlay, we're now seeing that our color image does not have a write only or read only tag on it. So looking at this, and I'm going to look at the shader first. That is all the same. As our input, we're doing our SunDisk image, which is our final result, which is our nicely blurred image. So that's going to be our SunDisk image. Don't know why I call it SunDisk image here, but need to give it a name. And then our second binding is an RGBA8 binding, because our output image is RGBA8. Even if you are on the Forward Plus with HDR, we are at RGBA8 here. Might change in the future if we have the whole 2D HDR and writing into the 2D HDR buffer. In that case, we might need a 32F, or no, sorry, 16 RGBA 16F buffer here. But for now, it's RGBA8. Set one binding 0, and we're just defining it as a normal image to the color image. Sweet. Then for our push constant, we have our render size and our reserved. I've named this reserved for some reason. Am I putting anything in there? No, I'm not even putting anything in there. I'm not quite sure if I needed to do that. Better safe than sorry. I think I assumed that I always needed to have a set of 4 floats. So yeah, I'm not using that, only the render size. That is our output image. That is because I'm actually using a sampler for this. So if I'm using half size, then obviously that image will be half the size of that image. But I'm capturing that because I'm using a sampler, and then because in this case, I'm actually using a or have I forgotten to do that? Oh, I always use linear samplers. Okay, cool. So my default is using linear samplers. So I'm using a linear sampler there so that it nicely ramps up, or smooths out the in-between values, which is more than enough because it's already a blurred image. So just simply linear filtering is more than enough for what we need to do. So yeah, we're loading our texture image in here, so that's our final result. Remember, we did swap it at the top, and then we went from our texture image into our Pong image for, okay, that's what we did in the first half of the radial, then we swapped them around. So now we went again from texture to Pong, and then from Pong back to texture in our two-step Gaussian blur. So we're still, our end result is our texture image. That becomes our input here. And we can actually look at the Renderdoc in a minute. And then the second one is then our color image. So here we're just setting our color image. We're setting through our push constant, and actually, you know, all of this is the same. With one small change, we're recalculating our render groups here because we are now working on our source render size, so our original render size. That will be the same as we're just running it, but if we were running it at half size, and so far we have been running all the steps at half the size, and then this step is run at full size. On YouTube, the blurred version looks way worse than the unblurred version. That's YouTube for you, mate. Yeah, I don't know if there's any way that I can make that better for YouTube, other than this looks very smooth on my screen. So, what can I tell you? That's YouTube. Well, it's a little bit more than YouTube. Like I said, I have been having a lot of problems with my internet. I'm supposed to have a 20 gig upload here, and I'm barely getting a 2 meg stream going. So I'm using 1/10 of my bandwidth here. And actually YouTube in the health setting is constantly telling me, like, you're at half the bit rate than you should be. You should up the quality. I was like, can't do anything about it because my internet just won't let me go higher. So yeah, sorry about that. There's not a whole lot that I can do about that in stream, other than say, trust me, the blur looks amazing on my screen. And I'd say, you know, verify it by trying this out yourself. Anyway, so the last step, what we're doing in here is a very simple shader. Same thing as always. We get our render size. We use our global invocation to get our value here. Check if we're out of bounds. If so, return. And now we load with our function image load. So we haven't used that one before, did we? Oh no, we might have used that in blur. We use our image load to load the current value of this pixel from our color buffer. So the value, the color that we rendered. What we're also doing here is we are loading our sun disk, but in this case, we're using texture loads because we're using a sampler. And even though this image might be half size, because we're using normalized coordinates by just dividing our UV by our texture size, that works. Don't have to do anything special. It'll nicely get a value. But obviously we do only have to need to get the red channel and there. And now we're doing a very simple calculation. We're taking our current color. Actually, we should say that here. We're taking our current color. We're multiplying that by our blur value. I'm upping it a little bit, and that's mostly because we're actually in linear color space here, and I found it looking a little bit better when I strengthened the value. So this might be something that we actually want to turn into an input variable, but whatever. So I'm calculating that, and I'm adding that back into our current image. So everywhere where our image is black, our original image stays untouched. And I could even, do I do that? No, I could even do a optimization here and checking if sun disk is 0 and just returning early to prevent an image store that just writes back the value that we already have. I could do that. Don't know if that's going to make a big difference, but that might make it slightly better. All right, Stefan, nice of you to join. I hope you have a great day. So yeah, so in this case, we're doing for every pixel, even the pixels that we don't need it. Yeah, that's fine. For our demonstration purposes, it's more than fine. Anyway, we end up writing the new value back. So this is an example where we are both loading and writing to our image, but because we are uniquely modifying a single pixel that isn't being touched by any of the other invocations of the compute shader, we can get away with this. But that's the big, the big if. That's the condition. Only in that situation we can do this. Else we would have to make a copy of a color buffer and then combine them. Or we go for the approach. No, even if you do a raster buffer with addition, you would still need to make a copy of your color buffer to read from while you're updating the final results. That's just the thing. Motion blur is possible. Yes, absolutely. As long as you have the motion vectors turned on, you can use the motion vectors plus the motion of the camera. You have to track that separately. And use that to create a motion blur shader with this. Absolutely. So that's actually something I want to research to see what exactly the best approach for that is. But I think actually motion blur using this is very doable. Could be some really cool stuff. And again, that's another effect where you really want to use reprojection and combine things with the previous frame, so that you don't have a bunch of overhead. And that might be a nice one to do because it's getting late already. It's nearly 11. So I just want to round this off, and we'll see if we can go on for another hour and at least do the basics of the other idea I had that I wanted to just implement to actually run through this. And we'll just add it into this project just for now, even though I want to make a separate project of it. But that would provide a template that people can do some extra stuff with. So, alrighty. Although I think for motion blur, you would probably do something like this. You would code it out like this, because I think for motion blur, you'll probably need quite granular control over which inputs you use and what you do with them, and possibly writing some things out to temporary buffers. But I haven't done a motion blur implementation for a long time. And the last time that I did motion blur, that was still in the time that we didn't have GPUs. So used very different techniques. And didn't look as good as the motion blurs that we have today. Okay, so we've completely gone through the process of this setup, explained each and every step, how it's implemented, code on the Godot side, the code on the shader side. Have touched on the fact that you have the scene and buffers and scene data objects that you can get from our render data variable here to get additional information. So for my scene buffers, we get a color buffer, we get our depth buffer, we can create our own buffers, we can get our motion burst buffer. There's a bunch more things that you can get to. If you have MSAA enabled, there's a few more things that start happening. But even if MSAA is enabled, by the time that you hit the post-transparent step, everything has already been resolved to the normal buffers. So it's really only if you want to introduce things earlier in the pipeline that you need to deal with MSAA. 4MB, I don't think we have, because the only thing that we're using motion vectors for right now is TAA. And I don't think that there's any blurring added to that. I think they're purely using that for aliasing. But don't hold that against me if I got that wrong. However, all the ingredients that you need are in there. TAA has the reprojection code that you need to make sure that you can reuse your previous frame result, so that you don't have to, because motion blur works very similar to the radial blur that we discussed at the beginning. The only difference is that instead of having the vector come from a central point, so in this case, the center of our sun, you're actually using the motion vectors that you read to see, you know, in what direction that pixel moved. And it's really the same effect as I was explaining with radial blur, that if you want to do that efficiently, you reproject your last frame's image. You then use your motion vector to offset all the pixels, overlay it on your current result, and that becomes your new image, which you then again, you know, keep around for next frame because you want to use that as the input to reproject next frame. And that's how you get that blurred out effect. And all you need to do is scale your motion vectors to increase or decrease the motion blur effect. That's my problem too for MB, is, you know, I know how to implement these things, but there's already so many things on my list, and I'm already behind schedule of a lot of them. So yeah, there's lots of ideas that I have and no time to implement, which is also one of the reasons why, you know, sitting here, I'm going over, okay, how would I implement that effect? How would I do, you know, the radial blur faster by doing a reprojection of the previous frame? How would I do motion vectors or motion blur, and really realizing that motion blur is pretty much the same effect as the radial blur that we did here, with the difference that instead of, you know, a fixed vector based on a center point, you're using your motion vectors plus your camera vectors added in. But in theory, it will be a fairly straightforward effect to implement. Famous last words. And, you know, maybe someone watching the stream will go like, hey, I know what Bass is talking about. That's really cool. I want to try and build that. And then they are going to get very angry with me because it turns out that there's a whole lot more to it, and they get stuck. But hey, at least I got the seed planted, right? Anyway, back to this. So yeah, from those we get that. Obviously, this is the other thing that is important, is that inside of the engine we are talking about the internal size and the render size, or the target size, I think it's called. Let's double check. Right, there we go. Where are we? That might. Nope. It's definitely on this one. Get internal size. And here's the other one. Where are you? You're not going to tell me that it's not in the help files. I don't know. That's strange. I'm pretty sure there should be a get target size in here. Anyway, this is for if you're using FSR scale, you know, upscaling or downscaling, or even bilinear upscaling or downscaling. The get internal size is the size at which we're rendering 3D content. And then get target size, wherever that's gone. Not quite sure. Maybe I forgot about it. You can definitely get it through your get render target, but then you would already have it because of the size of your viewport. So, but that's actually your output size. So, hey, Cyber. Well, we're at the end of explaining this part of it, but if I can stay awake, I might do a little bit more, because there was something that I want to scratch build tonight, and we'll just see how far we get. Anyway, so that's how you get to those. What else is in here? Oh yeah, just a little bit of the startup stuff, which is important to keep in mind. And this is really only important, although I would get into the habit of it, if you're running the rendering engine on its own thread, because when the rendering effects object gets created, it's going to call this init function, and that's happening on the main thread. And if you go and try and work with the rendering device while rendering happens on a separate thread, things start to get iffy. There are a lot of things in the rendering device that are thread safe, but there are also a lot of things where you can really screw things up if you're not running it on the normal thread. Now, there's other examples out there when we're looking at using compute shaders for certain calculations that are happening outside of the rendering thread, for which you are creating a local rendering device. Subject maybe for another stream someday. That can all be handled on the main thread, or you can even run that on your own thread because you're self-containing that information. But in this case, when we're looking at rendering effects, because they are inserted into the rendering pipeline, they have to run on the rendering thread. Now, the rendering callback that we've been discussing so far is always called from the rendering thread. So all this code runs on the rendering thread. No ifs, no buts. However, our initialization that we're doing here, if we would just do that over here, would be running on the main thread, and that could cause you problems. So what we're doing here is we're using this method of the rendering server, call on render thread, and we're giving it our method initialize compute. So this basically schedules that method to be called at the start of our rendering process. Now, the good thing about that is, it means that it runs on the rendering thread. The bad part of that is, it runs on the rendering thread. It doesn't run now. So you actually, whatever you do here, if there's a reason for you to have access to that information inside here, you don't have access to it until the next frame. So in our case with rendering effects, we don't have that situation. But I was using compute shaders in some other situations, and it did become a problem. So that is something just to keep in mind. There are a number of strategies to deal with that, but that's a topic for another stream. That would be way off tangent and take quite a lot of time to explain. However, cleanup is a bit more of a problem, because cleanup of this object kind of goes out of sync with what we're doing here. So in this case, we are cleaning up based on the notification pre-delete. And this is sort of linked to our queue free of objects, where we don't free objects right away, but we kind of put them onto a stack to be freed later on when everything's finished processing. So we're doing that here as well. And we're seeing that everything that we've created on our rendering thread in our initialized compute, we'll look at that in a minute, we're removing that here. And we're pretty much guaranteed at this point in time that the rendering has already cleaned up and forgotten about the rendering effect. If that's not the case, then that's something that we need to still improve. But so far, all my testing has indicated that this is a safe way to clean up. If you don't clean up, you'll leak a whole bunch of objects, which Godot will complain about to you at the end of the, end of running everything. So our initialized compute is run over here. First thing that we're doing over there is getting our rendering device, and we're remembering that because we're using that every frame. That thing never changes. Once it's a singleton, once it's created, you can use it. If we don't get a rendering device, we return at this point in time. Why would we not have a rendering device? Well, for instance, we're using the compatibility render. So that is another thing with the whole rendering effect system. Because we are joining into the whole rendering process, the code that we write is specific to a renderer. You cannot share the code between different renderers. You can't write code for the 4+ shader and expect it to work on the compatibility shader. Even after we implement similar functionality, if we get around to it, can't promise that we will, but it is something that we've talked about. If we introduce similar functionality in the compatibility shader, the implementation will be different. However, you can detect what renderer you're on and decide to, swap implementations at that point in time. We're creating our samplers. We have a whole bunch of default samplers that get created inside of the rendering engine. that I do intend to expose at some point in time. However, creating an extra sampler isn't really that much of an overhead. So here we're creating a sampler based on nearest filter and a sampler based on linear filter. I think we end up only using this one, so I can probably remove that one, but just in case I created them both. And then here is, 4 blocks of loading up our shaders and compiling them and creating the pipelines. Pretty straightforward. So that, I think, covers pretty much the whole implementation. So now about using the rendering effects. Now, in Godot, we have taken the approach to wrap all sorts of state for, how we're rendering a viewport into our environment. And the main reason we're doing that is because our main viewport, we don't have easy access to. We don't have an inspector that allows us to set that up. There's a couple of things that we can tweak through the project settings. But for that reason, we've introduced the whole environment concept, because that gives us easy access to everything. Did I not show the final result? I am so bad. So yeah, back into Renderdoc. There's our final result. So here you can see that as our input, we get our blurred sun disk. And as our output, we get our nicely adjusted image that is very, very dark. Why is it very, very dark? That is because this is the image before tone mapping is applied, before our conversion to sRGB is applied. So this is all in linear color space, which is always much darker than sRGB, and before we apply our exposure. So once those 3 are mixed in, we actually get the wonderful result that we see in the editor. Minus our box. Let's get rid of our box. That was just testing. Goodbye, box. Where we can see that those nice little rays are mixed in. And again, this effect works so much better when you're actually moving the camera around. And again, like I said, this is much darker because at this stage, we're still in linear color space. We haven't applied our tone mapping, haven't applied our sRGB conversion. We haven't applied our exposure. So this will be brightened up a lot the moment that we are applying those things. So that's something to be very aware of. But still, even here, if I zoom in on this image a little bit and get rid of those guys, you can see the rays kind of shining through. I hope that the what you call it, the YouTube compression doesn't completely remove it. But yeah, it's very hard to see in linear color space. I'm trying to think of Renderdoc doesn't actually have a toggle to toggle between those. So I vaguely remember that it had. Yeah, those are just the channels. No, that's... there we go. We do have a switch. So that switches between linear and gamma. So in gamma space, we can actually see that, yes, that image is properly colored. Now, again, in this case, we're just doing the linear to sRGB inside of Renderdoc. We haven't applied tone mapping and exposure. So obviously we have a lot more room to play with in our environment over here. We could start playing around with that stuff. I think we need to do can do something like auto exposure on here. That's very bright. But yeah, you can brighten it up. Where is tone map? So tone map is right now set to filmic. I don't know if Aces works a bit better. Oh yeah, Aces does make the effect much more visible. It's kind of cool. Although we can probably adjust our white balance a little bit. That doesn't do a lot of that. With it. Go back to filmic. Just look at the white balance there. Yeah, only when it goes up, right? There's not much. But again, the point is that there's lots of playing around to sort of make the colors pop. Again, like I said in the beginning of my stream, I'm a programmer. I'm not an artist. I am very proud that I can get the all the code in there, but I leave it up to people who have an eye for quality to then tweak the values and make it look nice. I just gave my sky a purple color and dumped a nice little scene from Sketchfab in there, and away I went. So after we create our whole effect, we give it a class name, Radial Sky Rays in this case. I've made it a tool script. If you don't make it a tool script, it simply means that it won't work in the editor. It will only run in runtime, which, whatever. But if you make it a tool script, then obviously it runs in the editor. The only thing that you really need to keep in mind is with this approach, the way that I've put this together, because I'm initializing everything on the init. That means that once this is created, that's it, it's created. So if I now change my GLSL file, or if I change the code in here, only some changes actually are directly applied. For some other changes, I have to restart the editor for it to rerun the initialization routines and recompile stuff. So that is a limitation of my implementation of a render effect, because I've decided to do it this way. I can build something in here that is constantly checking the GLSL files and recompiling them whenever it sees that it changes them, that they're changed on disk, which will be complete overkill because I don't need that when the game runs. I only need that when editing. But we're gonna do a little experiment where we're gonna do something fun where we will be able to do that to an extent, because we're gonna put the shader in Godot. Anyway, the important thing is that I gave it a class name that makes it possible for Godot to recognize this as a rendering effect class. And as a result, in my world environment, I'm going to just close these things to get it. So in my environment that I've created, you can see that there's now a new section called rendering, and under that we have a property called effects. We might at some point have other things that we add in here, but right now, that's where our render effects are. Now, obviously, this one, this becomes an array of effects, as you can see. So we've created a new array of effects. It has one entry, and the entry that it has is a radial sky rays object. So if I want to add another effect, I can do add, and I can just select them, and it should list all my effects that I have in the system, which in this case is only the radial sky rays. So that's the only one there. I don't want to do that twice. That would be pretty crazy. Probably would screw up a lot of things. So I'm not going to do that. However, the other thing that's really cool is that's an instance. That's a resource that I've now created. And I can actually expand that. And I see all my settings here. So obviously, in my preview, I can disable it. And we can see that all of a sudden, our effect changes. Turn it back on. I can turn my half size on, which you can hardly notice the quality difference in this case. It's still looking pretty damn good. And that is because with something like this, because it's blurred out and we have our linear effect there anyway, this is a really good example of an effect that you can speed up by running it on half size. Because in theory, that should save us about 75% of processing. So that's pretty cool. These settings that you see here are standard settings of the rendering effect itself. So obviously we have a type here. So this gives us the ability to run it at different stages. But you can't just simply change this, because obviously we have now implemented a post-transparent effect. So the fact that this is exposed is more that that's part of the properties of this object. We're obviously already setting the property in our init, so you can see that we're hard coding that to post-transparent. So every time that it inits goes to that, even if someone is dumb enough to change it in the world environment, that should leave, that's part of your implementation, what you want to do there. One situation where you might want to change this is, like I said, if you have an effect that needs to do something, let's say in the pre-opaque stage, which happens after we do our pre-depth rendering. You might want to do something there with the depth buffer so that it can run parallel to everything else. And then by the time you come to post transparent, you want to do the rest of your logic. In that case, you could use your effect twice, but set it once to pre-opaque and once to post-transparent. And then in your callback, because now your callback gets called twice, you can use the property, or sorry, the parameter. You can use your P effects callback type parameter to say, hey, if I'm in the pre-opaque stage, I need to do my depth buffer stuff. If I'm in the post-transparent stage, I need to actually do the rest of my effect. Sin, yes, Godot has a built-in post-processing stage that comes after this. So the last place that we can do is post-transparent before the built-in post-processing happens. And in the built-in post-processing, we apply our SSR and our SSAO, or the screen space reflections, our ambient occlusion, our indirect lighting, our glow, our fog, volumetric fog. All those are all done after us. The reason why we don't have something introduced that you could do after all the built-in things is because once the built-in post-processing has run, the end result is now in our render target buffers, which is our 2D rendering pipeline. So now we're adding our 2D elements on top, and we suddenly lose access to a lot of things. So while we are looking into also adding a couple of callbacks into the 2D stage so that you could do something after all the toe mapping and stuff is done, you might have the ability to do some more processing on the final end result. That just is a choice that we made, and to a big extent we figured that because we have so many different post processes, you would start to get into territory where I want to do it after the ambient occlusion but before we apply our glow, or I want to do it after glow but before tone mapping, which is impossible because that's one process. So we really wanted to avoid that situation. If you go to a situation where you want that fine amount of control, you might want to get to a place where you don't use the built-in effects, but you actually make them part of your own post-processing pipeline. And that is one area where, today that would be a big ask for a lot of people. But I think as more people start implementing post effects in the rendering effects, I wouldn't be surprised if we hit a moment where a lot of our own post effects are actually moved into the system. There's a couple of things that make that hard, but I think that would allow the flexibility that people really want in saying, this is the order in which I want the effects to be applied. Right now, with half of that being, or all the inbuilt ones being fixed, and then your own ones being flexible, it starts to get a little bit confusing. Yeah, maybe. I don't know. We kind of do that internally because we already have our GI and SDFG, our SDFGI. Jesus, that's a mouthful. SDFGI processing running in parallel with our def prepass. Yeah, maybe. The whole idea here also, of course, is also just to have a starting point. I actually introduced the post sky. That wasn't even originally in the spec, because that was the only way that I could do my own screen space reflection step. So yeah, I think that in the long run, it's very likely that we'll have additional callbacks. But I also think that until someone has a properly defined use case for them, I'm actually already concerned that we've added more stages right now than are practical, because really the post-transparent one is the one where we have the most ability to implement stuff. For a number of these other ones, there are more parts of the system that need to be exposed before you can really start making good use of it. A really good example, for instance, is that I might want to, and that's actually a good example for doing also before the def pass, is I might want to have a compute shader that modifies the vertex buffer. You know, that does some sort of deformation on a vertex buffer, maybe some sort of animation deformation. And you want to do that before even the rendering starts, but you want to do that as part of the rendering pipeline because you want to do that on the actual vertex buffer of that object. That's where I can see that we might actually want to have a pre-dep pass callback as well. So that's maybe one of the things that we want to have added at some point. But I do think that further improvements here need to be driven by use cases, and a lot of the use cases that I can think of, like the one that I just named, need a lot of other things to happen before they're viable. So, you know, one step at a time. I think sometimes we try to do too much in one go. Hey, Stratton, how you going? Nice of you to join. Anyway, so yeah, so here you can see which stages we currently have. And you know, like Ansir said earlier on, it would be really nice if we did some proper documentation about this, and that is definitely something that I want to add soon, where you know, we have a good overview of, okay, what are the steps of the that the rendering engine takes, and where are these callbacks happening, and you know, we have two more tick boxes here. There are a few more that we have depending on which stage you do, because we have some access to other things. For instance, if you and I can do this without any problems. Like if I go to post opaque, we can actually say that we want to have access to the resolved color or depth buffer. Obviously, if it already has those, cool. But if it doesn't, if nothing in the Godot processing needs the depth, you know, if you have MSAA enabled that needs the depth buffer or the color buffer to be resolved, then this will actually change part of the rendering pipeline and say, hey, my rendering effects wants it, so do this extra step, go and resolve the depth buffer, or go and resolve the color buffer. Let's go move the back. So there are some other switches that are based on what step you have, but yeah, needs motion vectors. So by default, motion vectors are only calculated if you enable TAA. But if you don't want TAA, but you do want motion vectors because you want to implement motion blur, the moment that you take that on, the whole logic in Godot to calculate motion vectors is suddenly enabled. It's only available in the 4+ renderer. That is an important footnote. We are looking into adding it to the mobile renderer, but right now only the 4+ renderer has got access to motion vectors. Same thing with normal roughness. So this is a tick box that has quite a lot of consequences. There's a number of effects that require this. Basically what this means is that during rendering, and this happens during the pre-def pass, we are not just filling the depth buffer, but we're also creating a buffer that has normal vectors for every pixel and a roughness value for every pixel. So we're basically creating one of the G buffers here, and it's not full deferred renderer, but we are creating an extra buffer. And there are a few steps as well where we even can trigger creating specular buffer. So we can trigger creating those, and there's a number of effects that require, like screen space reflections, need to know what the normal vector of every pixel is, so that it knows, you know, which direction to cast a ray to figure out if something's reflecting. I'm doing pretty good, Stradon. It's getting a bit late. I'm actually running out of time. I wanted to do another thing tonight, but it's already 11:30. So I'm probably just going to finish my whole talk about this and then chat to you guys for a little bit for anybody who's got questions, and then call it a night. And probably do a follow-up stream for my idea of what I wanted to actually create tonight. But, I think this was worth it. I think this was informative for a lot of people. I hope so. Anyway, continuing with this, I just wanted to show that all the properties that we added in are also available here. So here's our sun location, our sun size, and sun fade. Now, obviously, our sun location is updated in code, so we can actually. Oh no, that's if the sun changes. Hold on, where's my sun? Here's my sun. So if my sun changes, I can't do that and keep that open. That's a shame. But anyway, those values changed. So yeah, I can change them, but they will be changed back because I have a tool script here. This is also tool script. So, every frame we are updating that direction. But the other values I can affect. So I can, for instance, say that my sun, I only want a very small sun. So you can see that is suddenly a lot more simple. I can give it a much bigger fade size. So my sun is now much more an aura around it. For my radial blur, I can make this radial thing much bigger. So that makes the effect much less pronounced. Or I can go the other way. I can make that much smaller, which, well, I think my sun's gone too small to really see the effect very good. Let's make my sun a bit bigger again, because that's the downside of this. Is now you can see them come back again. I hope YouTube doesn't remove it too much, but yeah, you can see them sort of walking around that edge. It's kind of cool. So yeah, you can tweak a lot of things here. You can only do 8 steps of the radial blur. That makes it much more choppy. You can see the whole washy. I hope that actually survives, but I can really see the outlines of our blur effect now. So yeah, you can tweak the numbers and really. That's all fine. Yeah, my streams, as I said all the way in the beginning, I set a topic to talk about, and we'll see where it goes. I like an organic stream. I like it when we touch on other subjects, because it means that we're talking about things that you guys want to know. I can sit here for 3 hours and do a lot of talking, and everybody sort of goes like, okay, whatever. You guys suddenly start asking questions, and we suddenly go on to a completely different topic. That means that we are talking about something that people care about. So I'm all happy for us to go on some tangents and talk about some other things too. That's no problem at all. Anyway, so we have the ability to change those properties, and they will immediately take effect. They will be taken in. So you can tweak the effect in the editor. And again, like I said at the beginning, we have some limitations in when you're coding it, that you sometimes have to restart something because things only get loaded at the start. That is just a limitation of keeping your code simple and effective. Yes, you can solve those things, but it means that you add a lot of complexity to your render effect. And that once you've completed your render effect, and you say, here it is, because you can wrap this up, and you can take that folder, Radial Sky Rays, and you can plop it into another project, and there you go. You have your effect. You go into environment, create the effect, boom, plop it in, and it will work immediately. And you can tweak it, and it will immediately work. It's only when you're building it that it's a bit annoying that you have to restart stuff and that you have to go through stuff again. So I'm kind of going like, yeah, it's really not worth. Why is that showing on? Oh yeah, of course, because we whatever. Because of course we we had that cube and I deleted the cube while I still had the shader open. Oh well, that's okay. So yeah, so I hope this stream, and the stream will remain on my YouTube channel, so it can be rewatched. I hope this has given a good oversight of how this particular implementation works, but also serves as a good example of how do you build a render effect, and whether it is something like this or something completely different. A lot of it will be the same framework. You might have one or more steps that you go through. So for each step, you start a new compute pass, you do your shader, and put a barrier in place if needed. And you do your different passes. You might ping pong between a buffer that you've created at the start. And again, it's very important you create that at the start of your callback, because we cache everything. You will either reuse the buffer that you already had, or you create a new one if Godot, for whatever reason, has destroyed your buffer. Again, happens automatically when you resize the viewport, or if other things happen that make your buffers no longer viable, they automatically get removed, and you're responsible for creating a new one, which is a bit of a hassle with effects that are using reprojection, and then using the past frame and having an additive process, because obviously now you lost your history, you have to rebuild it. So for instance, for a radial blur, you get those first 32 frames where the radial blur gets repopulated. If you go down that path, again, I haven't implemented it like that here, but that will be my suggestion for an improvement. That's just the sort of thing that you need to take into account. And for a lot of use cases, those sort of edge cases where things, where optimizations have a negative effect, you also have to be realistic. People aren't going to constantly resize their screen while they're playing. Most people play their games full screen, so they're not even going to notice that is a startup time for your effect. So yeah. Carl, that's a good question, and I would say no. That needs something different, but it is one of the things that I have been given a lot of thought about, because especially the impact on stereoscopic rendering is quite big, because you're not dealing with just one matrix, but you're dealing with multiple that you have to either mirror or adjust, and that adjustment could be overwritten because we grab that information so late. So in a situation when you look at portals or mirrors or things like that, you're really looking at doing your whole render pass twice, one for your normal camera and one for your portal camera, for the other world, or or a mirrored camera for mirrors, with then a stencil applied or whatever to limit how much you render. And I was working on a document for a proposal that I had for that, to have that, because right now you would just need to do that with 2 viewports, and combining that is incredibly expensive, because you don't have the control over the camera that you want. I've actually got a proposal open for a long time to change the way that we do camera handling, but that's a relatively big job to do correctly, especially because we have a number of optimizations that make that difficult. Although that's also optimizations that you can't use in stereo rendering, so we already have ways to turn that off. There's a whole bunch of things there. But it really boils down to that we want to introduce the flexibility at some point in time that when you're rendering one viewport, that you can actually do the whole opaque pass and transparent pass twice, once for one camera, once for another camera, and overlay the results. I don't know what that's going to look like. I've got ideas. I've already written a whole bunch of things on paper that I still need to finish. but definitely this system is not really suitable for that. And I think one of the things that Radial is working on right now is something that's called acyclic render graphs. So that's a whole proposal that he has that I think Dario is going to be working on. That really needs to be done first before we tackle anything like that, because it gets very... the problem that we have with render passes and introducing an extra render pass for a portal or things like, if you want to do that efficiently, is that all these passes have dependencies and have to be linked. And with Vulkan, you actually have to predefine that all up front, which is really annoying. Yeah, there's a bunch of things that we need to tackle first. Sin, yeah, I can do that. But what would you like to know about stereoscopic rendering? Just want some background information about how it's set up, or specific to Godot? What's because most of it, because that's one of the things that is kind of a what's the right word? Kind of a mandate with how we build Godot, is that we try and remove as much of the internal complexity as we can. So almost all of the stereoscopic rendering implementation is completely hidden. The only places where you see it that is now exposed is rendering effects, because you really can't avoid it at that point in time. But yeah. Yeah, I'll gladly talk about that, but I'm sort of going like, what exactly do we want to know? That's all built in internally. That's actually the big change that we did in Godot 4. In Godot 3, we went old-fashioned render left eye, render right eye, completely used hidden from the user. So basically, the way that we have done it is we've introduced a thing called an XR interface. That's an abstraction for the XR runtime that is being used. So we have a tilt5 interface that implements the tilt5 driver. We have an OpenXR interface that implements OpenXR. We have an ARKit interface that implements ARKit, although that one still needs to be ported to Godot 4. We used to have an OpenVR one for that. Actually, it's still around, but I don't know if anybody still uses it. And when you, and that's basically, I don't know if you've looked at the code in Godot, but the moment that you, on a viewport, when you enable use XR, you're basically saying to Godot, for this viewport, ask the XR interface what the setup is. And the XR interface is then going to say to the viewport logic, like, hey, I want you to render in stereo. Here's the projection matrix for the left eye. Here's the projection matrix for the right eye. These are the offsets that you need to use so that your IPD is correct. And that turns on the stereoscopic rendering in Godot. Now, as we looked at earlier on in the stream, when we looked at the render data, the scene data object, where we saw how the projection matrices were stored, there's two things that are very special to Godot that I don't think any of the other engines do. One is, well, actually one thing that other engines will do is to combine frustum. So taking the left eye and the right eye frustums and combining them into one big frustum for culling purposes. So we cull only once. So we create our list of data objects only once, not data objects, geometry objects only once that we want to render. But we also do a single render pass. So everything is done with an extension called multi-view, which is by now pretty well supported. There's really the only problems that we've had is, maybe on very old phones that you want to use with a Gear VR or something like that. But who still has a Gear VR nowadays? So we use a thing called multi-view, and that means that when you create a render buffer, you basically say, these are the number of views that I want to render. In this case, 2, because we got one for left eye, one for right eye. The texture therefore gets 2 layers. And then when you execute a render pass, it basically internally in the driver duplicates the draw call and runs your vertex shaders and your fragment shaders for your left eye and then for your right eye in parallel. So yeah, that is pretty much the most optimal scenario that you can do. And we do that both on the compatibility renderer and on the Vulkan renderer. So it's automatic. It's just built in. All right. It is for me 11:45. So I'm leaving the floor open for another 15 minutes. If anybody else has more questions. While on the XR topic, can I use the UE system in world space? No. None of the 2D objects can be rendered in 3D. To be exact, we actually disable the 2D rendering when stereoscopic rendering is enabled. What you can do is render all the 2D elements to a separate viewport and then use that viewport on a texture. And the other thing that we're still working on is using the composition layer system in OpenXR to actually do that on the compositor side. And that's specifically like on Quest. That's pretty cool. That if you, it's like how the Quest UI also works. Because you can now render your 2D UI at pretty normal resolution. And because of the way that it is projected in front of you, as long as you are, well, in those UIs, you're normally in front of it. It's done after lens distortion, so it keeps its crispness, crispness. Jesus, can't pronounce that word. It stays very crisp. So that's something that we're still working on. Right now, you would have to project it on a 3D object, and that's how the UI works in XR Tools, for instance. We have in XR Tools we have a component. Actually, I can quickly show that. It's not really a problem. I do need to go back to an older version of Godot. I think I still have my XR Tools in 403 at the moment. Yep. Because that's the lowest version we support for XR Tools at the moment. And then we go to scenes, and what is the one that has the UI in it? Why can't I see you? Which one are you? Is it the interaction rules? No, it could be. Yeah. Is it? No, that just has the 3D interactionals. I can't see it. Why can't I see it? Is it pointer demo? Probably pointer demo. Yeah, here we go. So here you can see that there's a 2D UI. So if I look at this one, nope, that's not. That's just a helper. I need the scene itself. Or did we? Screen. Which scene are you showing? Display. Content. Keyboard test screen. That's the one. So yeah. So here we have a 2D scene in Godot, and it is then using our viewport 2D, and this one is extended, but it's using our viewport 2D and 3D scripts to then display that on a screen that you can then interact with. Oh, that's the wrong one. So you got a little keyboard here that you can interact with and stuff like that. So that's the way that you would do a 2D UI in Godot at the moment. That's how most people currently deal with 2D UIs. And that, the nice thing about this is that it's a proper surface in 3D space, so that it actually, it doesn't make you motion sick or anything because it's anchored to your view. It's actually in space, and you can make it follow you, or you can make, you can child to the camera and get some nice logic going that it follows you around or something like that. But that's a way that we currently do it. I'm looking forward to people implementing a proper UI implemented in 3D. So we obviously, I'll just close it. We obviously are working on a number of objects that you can extend and customize that do things like buttons that you actually can press with your fist and stuff like that. But I can see more things working at some point in time. The other thing which is really important is if you just want the UI to show things like labels, we actually have a label 3D object that just prints text in 3D space, which is kind of nice as well. Alrighty. Anything else that anybody has as a question? For anybody, by the way, who's new here and who hasn't done much in XR, this is our XR Tools toolkit, which implements, you know, basic mechanisms that you find in many XR games. It has a whole bunch of demos in there. So this is our interaction demo, but for instance, what's a nice one? Like Sphere World is pretty cool. Oh, I need to zoom out a bit. Boom. So this is a sphere in space that you can walk around in. So this is an example of a world where gravity isn't always down. It's always towards the center. Well, it is down, I guess. But it's to the center of the globe. And you have all these funky shapes that you can walk on and stuff like that. So it shows, you know, a bunch of movement mechanics that we have and stuff like that. We have a demo where you can pick up lots of things. You can pick up hammers and balls and blocks and do all sorts of fun things with that. So, yeah, there's some really nice things in it. Yeah. Rather, you are implementing the Pico 4. Do you have any info? It's already there. Where are you? Oh, damn, I've got my Tilt 5 on top. Here's my Pico 4. So yeah, Godot runs pretty decently on a Pico 4. I've heard some people have run it up on a Neo 3 as well. I don't have much experience with that. Yeah, Pico is pretty on board with us. They've helped out with a lot of things. So, you know, there have been some issues in the past around Vulkan support. That's all fixed now. The 4.2 has got the new action map entries for Pico. So there's a bunch of changes coming there. 4.1 is still using their unofficial controller bindings that they had before. You know, they were able to match the standard and get them accepted into. I've actually got a video, I think, even for. I think I even have a video for Pico. This is up next. Oh, here. This one. Getting started with Pico 4 on Godot. So it's a little bit dated, but because we've changed all the loader stuff. So the loaders are slightly different. Have I got the loaders installed in here? I don't know. Probably not. No, this is still the old one, but I don't have the loaders installed on this one. This is I always keep my XR Tools repository on the earlier version that we support, so that I can test that it still works on the earlier version. We're about to move with the next release of XR Tools. Well, with 4.3 from XR Tools, we're going to bump it up to a minimum version of 4.1. We're waiting on on 4.1.2 to be released before we do that because of a bug that's in the compatibility renderer. But anyway, yeah, bottom line is definitely on 4.1.1, Pico should work decently. Again, the problem is that compatibility does have that animation bug. That's fixed in 4.1.2. Well, it should be fixed in 4.1.2 if it gets cherry picked. So that's the only one, you know, because you really do want to run on compatibility renderer at this point in time. That's where we've got the experience to make it run well. We're still figuring out a couple of bugs in the Vulkan renderer, a couple of issues in the Vulkan renderer. And I think it'll still take a little bit of time before we really figure it out and nail that. So yeah, you can, you know, there's a bunch of people on the Discord who are using the Vulkan renderer, the mobile one, pretty efficiently. But if you really want to hit your 90 FPS frame rate, right now the compatibility renderer is the one to choose. Oh, my throat's going a little bit. Let me fill up my glass again. And then we're slowly going to make it into the stream. So anybody else have any more questions? Or Sid, if you have more questions, feel free to ask. Long term, for some kind of higher level rendering API, it is that Unity where you can draw a mesh to render target. Yes, actually, I don't have the link handy, but Rados did a proposal a week or two ago, probably even a bit longer already, for, I can't remember what he called it. But he wanted to add an API to the rendering server to do you know, basic manipulations on textures so that you can lead render to texture and, you know, just draw some easy stuff to it. You can do a lot with actually that's actually a nice one as well. Let's see, close this, save. Because the where are you? Get the purchase list. That's what I was looking for. Do I have it? Where are you? Oh, that might not even be checked out. Come on. Demo. Oh. Demo projects. Where are we at rendering effects? Which one have I got? Oh. Yeah, that might be the right one. Why are you not in my list? No. Sure. Why don't I have it in my list? Maybe I accidentally removed it. Actually, that might still be empty. Git branch. That one is the one that I wanted. I think that texture directory is probably empty. And that's why I probably removed it. Project. Test. No, it's not tests. It is Godot demo projects. This one actually is a PR right now on the demo projects repo. Custom shaders, as in for materials? No, actually, I recommend everybody starts using custom shaders over the normal shader material, and then keep things as simple as possible. Chris, I'm going to answer you in a minute. Let me just quickly go and run this up. So this is a standard little, very old school water effect. The basis of this effect has been around since, I don't know, early 90s, probably. But I implemented this in with the new compute texture logic. And I just wanted to point that out because while Paper Marty's question is indeed very valid, that we need a simple API to do simple modifications on a texture to do certain effects that you can really coolly do with I can think of like a terrain drawing has been named quite a lot, where you just draw on the texture where it has a response from someone drawing their mouse over a terrain, and you change the height map and that sort of thing. But this is the version where you're using compute shaders to do exactly that. Like I said, this example is already a PR on our demo repo. It'll probably be merged once 4.2 is released, because we usually don't merge them until we have a build that actually can run it. But the basic premise of this is that I have a texture that I create through the rendering device. In this case, I create 3 because I'm using them in a round robin, but in principle, you can just use 1. And this shows how you can manipulate the contents of that texture. And I'm doing this on the rendering thread, but you can actually also do this, just on a local rendering device to modify the texture. And then that texture is then used as a normal texture object to be drawn on a normal shader. So when we look at our water image here, we can see that we have a texture input here, a normal texture input here, which is an effect texture, which is of type texture 2D RD. And once we start up, we're going to assign our compute shader texture to that texture object, and that is now used internally. And that means that you can use the whole render, the whole compute shader approach to do drawing to the texture. Now that's the low level approach. That is the, hey, I really know what I'm doing, so I can do this. And then this is something that for doing height map editing, this is perfect. This is really the option on steroids. But we are working on an API that does a much simplified, here's a texture, draw something else on top of it. All right. By the way, one other thing, I've abused viewports for that in the past, but there's some limitations there. So yeah, same pitfalls for writing custom shaders. Other than if you do something very performance intensive in your custom shader, but that goes for any shader, you can enable very performance intensive features inside of Godot itself as well, and get into trouble. But on generally speaking, I recommend anybody who is really after getting the last ounce of speed and performance out of XR is set up your textures where needed with the standard material. But then as I did at the beginning of the stream, you then go to the drop down and you say convert to shader material, and then you get the shader code that Godot creates, and then get rid of all the nonsense, because there's a lot of it's generic code that Godot creates. So there's a bunch of things that it does standard, that it does on the assumption that you might assign a roughness texture to your material, or things like that. So there's more code in there than the shader really needs if you just have a simple texture mapped objects, for instance. So there is room for optimization in the shader, and it's worth doing. So yeah. So, Chris, there's a lot of new Unity users joining, myself included. What are the best ways we can help? Is there anything you'd like to share about the Godot software or the culture with former Unity folks? There is a lot, and I could dedicate a lot of time to that, but the most important things that I would like to impart, first of all, Godot is FOSS, and FOSS has a lot of advantages, it also has disadvantages. The most important aspect of FOSS is to realize there are only a few of us that are paid by the foundation. And the people that are paid by the foundation are paid to work on very specific things, often as a result of a request from or an often given request from the community, or like me, I was, for the time that I was funded through Meta, 90% of my time was focused on XR. Unfortunately, right now not. I had to scale that down because we're no longer sponsored by Meta. So the good thing about that is that I'm doing a lot more on the rendering side and helping out there. But my love is with XR, so I'm hoping to get more there. But yeah, it's me, and I think there's 8 people right now on payroll. Emmy is one of them, but he is our executive director, so he doesn't do programming. Well, he actually does because he builds Dialogic, but he doesn't do programming on the payroll of Godot. He manages the projects. So a couple of guys who are part-time, Fernand George is well known for his work on GDScript, and there's Bruvs, who's working on, I think, iOS support and some other things. But my point is, there's only a few of us. The majority of the work that is being done in Godot is done by volunteers, students, people who are just doing it for the love of it, etc. And there are a number of people who are working on Godot because of the company that they're working for. They're either working for a game company and building a game in Godot and therefore contributing, or they're working for service providers like Ramattack or W4 Games or Lone Wolf or any of the other, Pineapple. Let's not forget Pineapple Works. They're doing amazing work on console support. Bottom line is, the majority are people who are either volunteering their time or they are working for the things that they need, either to complete their game or to service the clients that are completing their games. We're not a company like Unity with 100 developers purely there to do what the Unity clientele wants them to do. Most people are doing it out of love, out of enthusiasm. So treat them with that respect. That's really what I wanted to get down to is, don't go and send to someone and say, I need this because else I can't switch. And then, sort of go like, you're talking to someone who is putting hours and hours and hours of their spare time into getting something to work. Treat that with some respect. So that's definitely one thing that I definitely want to say first, because luckily most people that I deal with really understand that and really see that and really respect the work that people are doing, and are just really glad that people are putting so much of their effort into something like this. But there are people who, for lack of a better word, are overly entitled. And that hurts. That's I've suffered from that a few times, where I'm sort of going like, I've given nearly 7 years of my life now on XR support of Godot, and 5 of which completely voluntarily. Only the last 2 I've been paid to do this. So yeah, it can hurt. So that's one thing that I wanted to say to any newcomers is, treat the people who work on this stuff with respect. The other thing that I really want to say about our community is you will find the vast majority of our community to be incredibly welcoming and incredibly free-giving with their time, especially in many of our communities. And I hope everybody's seen that on Twitter, because normally Twitter is accessible, and I have been really amazed about the level of help that people have offered on Twitter, and the welcoming nature that most people have given, you know, dealing with a very difficult situation, especially with a lot of Unity people being very emotional. You know, there's a lot of people who are fearing their livelihood at risk. So things can get heated, and things can get, yeah, I can understand people who are in that situation, who are latching out and trying to really go like, you know, I can't continue my livelihood unless I find a solution here. Why, you know, why can't Godot be more like Unity so that I, you know. So that is a part of it. The other part, which is really important over FOSS, and something that I hope that we get more of. I'm always fond of saying that FOSS is a numbers game. You know, let's say that 5% of the people who join the community, I have the skills and the time to improve the project. So if 10 people join, we might get lucky that one of those 10 people actually contributes. If 100 people join, then yeah, we're getting an influx of people who also can help out. If 1,000 people join, all of a sudden we start to get people who are contributing on a larger scale. And the nice thing that I personally believe, when you are in a situation where most of the work being done on a game engine is being done by people who are actually doing work, who are actually making games, you tend to get changes that are battle tested, because they are made to a very specific need. While when you usually look at, you know, more generic solutions where just someone is doing the work because they're paid to do the job, very often the quality level is very different. The insight level is very different. So, you know, those are the sort of things that I'm really going, you know, the more people step in, and the more people also go like, okay, this isn't perfect, but I can see where it's going. And even better yet, I can help out it getting there. The better FOSS gets, and the better Godot gets. So that's where FOSS starts showing its strength. Once those numbers start increasing, and people give it a chance, and people are willing to accept the rough edges, and sort of go like, I can work around those, or I can contribute and make sure that those rough edges get solved. And that's not for everybody. Like I said, you know, you might get 5 people out of 100 who have that skill and have the time and have the inclination to help. But you have those 5 people if 100 people join. So, okay, let me catch up with everything that has been said so far. Oh, and donate to the project. Of course, that has to be said, right? Although, actually, that does bring me to one other subject, and that I think I've mentioned before as well, and that is specifically for you, Chris, seeing where you're coming from, and people like you who are in positions in the industry like you, is talk to your bosses. If you are working for one of the vendors, and for me, that obviously in the XR space means you're working for Meta, you're working for Valve, you're working for Apple, you're working for Magic Leap, you're working for, you know, Pico, and while we already have really good relationships with a number of those, the more people internally there, and especially decision makers, and they're here like, hey, there's this really cool game engine, Godot, I'm playing around with it, and, you know, you guys should really take notice, we should invest in this, and and I'm not just talking about investing money-wise, which obviously is something that's really nice. If we get more funding, we can do more. We can hire more people. We can get higher quality people in, and we can strengthen the core of the application. But it's also having access to those vendors. Even though we have a really good relationship with Meta, I would love to have engineers look over some of our code and go like, hey, this is what you missed. This is why something is not performing on our hardware. We have some of the vendors that do that, including Meta. Let's be honest about that. I obviously have some people that I've met over the years that are definitely very welcoming and in looking things over and helping out. But those sort of things become really important. That if you are working for one of those companies, at the very least, let them know your interest, because the more they hear that people are interested in Godot, the more serious they take us. But also, see if they can help in some way, shape, or form. So. All right, let's keep catching up. So, Carl, thanks, Bastian. Very informative stream. Happy to paint a clearer picture of Godot's rendering engine where documentation is not yet available. Yeah, and again, on documentation, we are strapped for time. So I want to make a lot more documentation, but there are only so many hours of the day, so hopefully we'll get there. The nice thing that I really like on that subject also is that as more people join to help out, and more people join like the rendering meetings or the more in-depth discussions that we're having, or join in on the proposals and discussing the proposals, there are more and more people who have really good insight into how things work. They can also help out by writing that stuff down and sharing that stuff, and at some point using it as a foundation for documentation. Yeah, James. So yeah, well, we're on the tail end. But this stream again, I said at the beginning, this goes for all my streams. They stay on YouTube, so you can always rewatch them and go through it. Foreman, it is possible. Let's be very clear. We have a very good relationship with Meta. Meta not continuing the sponsorship that we've enjoyed for 2 years is a direct result of the situation that we have in our industry right now. It's not because Meta sort of went like, we don't like you guys anymore, we're not going to give you a grant. It is because the market conditions just meant that they had to they had to leave it for a bit. And that's fine. They, like I said, we still have a good relationship. I just got a Quest Pro from them. Actually, they send us 3. They send one to me, they send one to Malcolm, and they send one to David. Obviously me for my work, Malcolm as my partner in crime for extra tools, and David for WebXR. So that's really appreciative that we can work on their hardware, and I'm pretty sure that once the Quest 3 comes out, that'll eventually we'll be able to get a Quest 3 to test with, and there's every likelihood that Meta at some point turns around and says, "Hey, Godot, we're in a position to help you out again." And we want to talk about another grant. This is very, very likely. At the same time, let's be honest. I'd like other vendors to also consider that. I much rather have a number of vendors giving us smaller amounts of money. Let's say that they, instead of doing, what was the last grant? I think 100K. If 3 vendors give us, or 4 vendors give us 25K, we still have the same amount of money, but we don't have our eggs in one basket. So yeah, it'd be really cool if vendors look at our new developer fund that we just released, or just put together, and see if they want to help out in that way. I find it strange that some of us Unity folks demand better C# support. It's like walking into someone's house start. Yeah, and again, you know, it's I've had a few discussions like that as well. I'm a C++ guy. I got into GDScript when I got into Godot, and I had to swallow too because I'm not a fan of Python. But the GDScript is not Python. It's the syntax might take some hints from it, but it's a very different beast. And I think the big thing that people forget when it comes to GDScript is that it's very tailor-made to what Godot is, but it also has a, you know, it really is one of those use the right tool for the job things. You know, I wouldn't use GDScript to load in a million vertex object and do a whole bunch of manipulation on it and then expect that to be fast. That's not what GDScript is for. GDScript is to control your game. You know, to write some AI logic, to write some glue logic. Godot's strength lies into really making good use of the node tree. And, you know, there's so many things that are, that work out of context, and I can't remember the right word for it, but there's a lot of stuff that you can make work in Godot without even writing a single line of GDScript, just by linking things up and making good use of, you know, things like the animation tree and stuff like that. So on one side, I agree with that statement. Like, why in heaven's name are they so worked up about it? You know, why, you know, how can they feel right about making demands like that? But at the same time, I get it. You know, you're working on a gaming Unity, especially, you know, when you are looking at many independent developers who are building their game on a shoestring budget, hoping that when they release it, it'll you know, it'll make a decent amount of money, but then seeing most of that money disappear in you know, Steam fees and taxes and other fees, not having much left over at the end, but probably making enough to you know, to hit those thresholds. For those people, all of a sudden it doesn't make financial sense anymore to continue, but they've already invested all that time in a game. So I can really understand that people who are in that boat are feeling very overwhelmed by the situation. And when they then hear, okay, well, if you don't want to use Unity, you can go Unreal, but you have to you know, you have to learn either C++ or you have to learn Blueprints. Or you can go to Godot and you have to learn GDScript. Well, it has C# support, but it's very different than C# in Unity. So you still have to relearn a lot of things because you also have to relearn Godot. That's a tough realization to hit. And while I know that if someone like that, when they have a type of game that Godot can easily be implemented in Godot, that they're gonna, you know, a couple of months from now, if they make that choice, they're probably gonna be very happy with it. And it depends a bit on what sort of people they are. Come back to that in a minute. But I can understand that at the short term, it's very confronting what they're going through right now. So I'm on one side a little sad that people react on that, but on the other side, I'm sort of going like, I can get it. You know, they're in a really tough spot. Their world is falling apart, potentially, if everything goes through in Godot, or Unity doesn't backpedal on things. And, you know, you lash out. You get, you know, you get beat down at that point in time. It's understandable. It's, you know, doesn't make it right, but it's, I can understand it. I can understand that. And I think it's only going to be temporary, right? Yeah. And that brings me back to, you know, the subject of what sort of person you are, what sort of programmer you are. The thing that I have learned doing Godot for 7 years is Godot either clicks or it doesn't. Either you get the philosophy behind Godot and you start working according to that philosophy, and you start suddenly seeing what makes Godot really good. And you start seeing that you can build things in Godot way faster than you're used to. Or you're the type of person that doesn't agree with the way that Godot works, and you try and retrofit your way of working into Godot. If you're that type of person, nothing wrong with that. But Godot is probably not the tool for you. You know, Godot has a philosophy and a way of working that if you adopt it, sky's the limit. If you resist it, you're going to be very unhappy. That's really what it boils down to. And again, you know, that doesn't, it's not a right or wrong question. It is whether you're comfortable with that philosophy, with that way of working, or whether that's not the way that you want to program games. And you're better off in an environment that that has an approach that agrees with you more. And that's okay. That's fine. You know, it's people have different people are wired differently. People look at problems differently. People solve problems differently. That's fine. All right, let's see. Where am I now? I wouldn't. Yeah, you wouldn't dream of using GDScript. Okay. On that. Oh, there's the webcam down again. Dang it. Camera. I hope my new camera comes in tomorrow. That actually my camera itself looks good. Maybe I should have bought a new cam link. I don't know, but yeah. So on the subject, I wouldn't dream of using GDScript. I totally get that, and if you are happy to learn Godot with C# and you're more comfortable with that, good on you. That's fine. That's perfect. If that is, you know, if that is the way that works for you, you're not going to hear any complaints from me. I am going to give you the advice, though, is to not rule it out before you try it. And the best advice that I can give for anybody coming from Unity who wants to get into Godot is, instead of trying to do what you're used to doing in Unity, or even trying to immediately grab the game that you were building in Unity and now going to build it in Godot, instead of that, is just take a big step back. Go on to GDQuest's YouTube channel, or Kids Can Code, although some of his content is getting a bit old. Although he's making new videos now, which is cool. He's a really good teacher. Heartbeats is a good one. There's a bunch of others. Game Endeavor, and run through a few of their tutorials. Just, you know, even if you're someone who wants to make the next big 3D game, build one of the little 2D tutorial games. You know, it'll take you half a day, maybe a day to get through. But it will show you the ideas behind Godot, and especially if you do, you know, if you follow tutorials like GDQuest, who is really good at explaining the concepts behind Godot. So I would definitely recommend him. But there are others who do a really good job at explaining the philosophy behind how you build Godot games. I can really recommend spending that, you know, half a day, 2 days at most, going through a number of those things and just doing it the Godot way. And heck, even just using GDScript, you know, even if after those 2 days you sort of go like, that's nice, that was cool, I'm going back to C#, perfect, fine. But at least you get that experience, like, okay, this is the thought process that goes behind how do I do things in Godot. Proper use of signals, proper use of subscenes, proper use of, you know, instead of coding stuff, figuring out, okay, what are the objects in Godot that actually do this for me? And once you get a grasp of those concepts, you'll find out even if you do the work in C# after that, you'll have a much better understanding of how you can make a good Godot game. Senior Super Spade, yes. One is he's one of the original developers of Godot, together with Ariel Mansour. Well, Ariel went off to build lots of games and other things, and Juan eventually kept hobbying on Godot, made it, they together they made it open source, and he kind of brought it to where it is today. And today he is, he's sort of more like a technical advisor. He's still our technical lead. So he is obviously doing a lot of things like for instance, rendering effects is his idea. He spec'd it out and I built it. But my point is, he knows Godot. It's the thing that he built. It's grown much bigger than he ever imagined, probably, and can't make him more happy. He's a swell guy. I've met him a couple of times. Really cool. So yeah, in essence, what you're saying there is true. But I'd like to offer a little bit of context about that, in the sense that the way that I look at it and the way that I will say is Godot is needs-based. And it harks back to what I said, I don't know, 20 minutes ago, about who's working on Godot. Majority are volunteers, and a lot of people are people who are working on their own games, using Godot to build their games, and then contributing the fixes and improvements that they are making because they need those to complete their game. The great thing about that is that the changes that are flowing into Godot are generally changes that are needed to build games. They're not just someone who says like, I woke up this morning and it would be really nice if I add a button in the game that turns everything purple. Yeah, nobody asked for that. It's nice that you thought that was a good idea, and maybe you like the color purple, but that we're not going to add that button in. No, most of the work that actually gets accepted into Godot is work that comes from the need of the person doing the work. That in game development, that means that you are also meeting the needs of dozens of other people who are working on similar games and therefore have similar problems and are trying to solve that, and that your change suddenly helps a whole bunch of other people. That's great. The problem is there is a counter argument to that. And that is that if I am not a programmer, but I like to make a game, and I find Godot and I find that GDScript is easy enough for me to do the logic that I want, and the philosophy behind how you build Godot games appeals to me enough that I can actually build the game that I need. But in order to complete my game, I need this one feature. And I then go to the community and I say, hey guys, I really need this feature to complete my game. It gets hard to find people to help you implement that feature, especially if that is a feature that nobody else needs. And that's where things get frustrating and heated, especially when the feature itself is good. And that's a really interesting conundrum when, and actually a problem that Unity has as well. One of the, there's some overlap between Godot and Unity when it comes to these things. Both Unity and Godot are jack of all trades, general purpose game engines. Unlike Unreal, which is a game engine that is very specifically targeted at a certain vertical market of games. It's a fairly wide vertical market, but it's still, there is a certain set of genres of games that Unreal is very, very good at. And the same goes for a lot of in-house engines that a lot of AAA studios use. And it is because they can concentrate on that one or limited amount of genres and become really good there. For a generic game engine, there are a lot of things that you can do, and it would make the experience for a couple of people really nice, and everybody else suffers. And it is those sort of changes that if you are needing that sort of thing, if you do not know how to isolate that and make that something that can be tacked onto the main engine, you're going to be in trouble. And to some extent, you know, that's also called a spade is, you know, the people who are going to run into those things are generally the people who are upmarket, right? AAA studios, people who are, you know, really getting, have the need to get optimizations into their game that are very, very specific to what they're trying to do. For most small studios, indie studios, generic game engines actually do a really good job at meeting the needs for those. But you got to figure out how to fit your goals into the constraints of a general purpose game engine. Instead of going, I really need this to improve, and I don't care that 100 other people are going to be worse off because I can make my game. So that's part of that problem, is where the work is done primarily by people who need that work done. You know, and again, it's not that strict. You know, it's a generalization. It's almost a stereotype on what we're doing. Now, don't forget, there are so many people involved in Godot who are purely contributing to Godot because they enjoy doing things. And those are the type of people who will actually go like, hey, someone needs this. This is actually a really good idea. If it's a good idea and it's fun for me to implement, I'll do it and I'll implement it. Or, you know, if you are a studio that actually has a budget, you can go to one of the service providers, like, you know, like I said, Rematech, W4 Games, Pineapple Works, in the XR space, what they call it, Majira. There's a whole bunch of them. And you can just go to them and they can say, I need this added to Godot to complete my game. Can we sit around a table and see, A, am I indeed wanting something that makes sense? And B, if it makes sense, what is it going to cost me to add that feature? And how are we going to manage it if it can't be upstreamed, if I need to only have this feature in my copy of Godot? Because that's the thing that people forget, is Godot is FOSS. So you can do with it whatever you want. If you know, if you have a need for a very specific feature in your game that doesn't get merged into the general purpose engine because it is too specific to your needs, then you have a fork of the engine that has the additions that you need in them. And yeah, that has a bit of management overhead, but if that is what is required for the success of your game, then that is something that's doable. Anyway, that actually, that reminds me of another point that I wanted to make, going back to Chris's original question. One other thing that is important to know about our community that is very often overlooked. Godot is worldwide. And the fact that Quan and Ariel are the founders of the project actually is a very important part of that, because they're from Argentina. They are native Spanish-speaking people. And that means that English is a second language. And that goes for me too. You know, my English is pretty good, I hope. But I'm Dutch. I sometimes express myself incorrectly, not because of what I want to say, but because I'm used to Dutch, to the Dutch way of expressing myself, and I might not get the final minor details for every English saying. And that goes for the whole community. We have lots of people in the Middle East. We have lots of people in Africa. We have lots of people all over Asia. Obviously, we have people here in Australia. We have people from all walks of life, all different backgrounds. Many, probably the majority of people who are not native English speakers who are contributing to Godot. So I would also like to caution everybody that if someone says something that might be a little too direct or that might look a little bit out of context, maybe ask yourself whether it is that they are saying something bad or rude, or whether there's just a language barrier here and they're just expressing themselves in the wrong way. They're trying to say the right thing, but it's not coming across. And even between English speakers, because when I look at some of my Australian friends here, I'm pretty sure that most Americans or most people from the UK will misunderstand them very quickly, because there are some very interesting idiosyncrasies in our here in Australia. So I think that's a pretty important point to point out. Is, especially on Twitter. Come on, the number of times that I've expressed myself on Twitter and then people completely misunderstand what I say because I'm trying to communicate something because I don't have a blue tick, so I can't write large pieces of text. I do everything in little fragments, and then I'm also partially dyslexic, so sometimes I forget a word or I turn a word upside down and I need to go back and edit that, and you're not allowed to edit on Twitter, so screw that. Yeah, kind of important. Terrain editor, would you speak about GD extension? What about maintaining add-ons? All right, so there are a bunch of terrain editor options. I'm famous for making a case for a long time that I don't believe terrain editors should be part of Godot. They should be plugins. They should be external. My main reasoning for that is that there are vast differences in implementation between different terrain systems, depending on what your needs are. A terrain system for an open world game looks completely different to a terrain system for, a level-based game, or, that sort of thing. There are lots of very different techniques in terrains. A terrain system can be completely different if it's targeted for PC VR or for mobile. Mobile has very different constraints than PC VR. So I'm a strong believer that terrain systems should be plugins, and I'm a strong believer of an ecosystem where we have a number of different terrain systems for different use cases. And for a long time, a lot of people ridiculed that opinion of mine, and that's fine. People are allowed to do that. But I think that we're getting to a point where those terrain systems are starting to evolve. So we have, what are the names? Start with a T. Corey is one of the developers there. Well, a terrain editor that came out a few months ago, and a lot of people were very impressed with, and that's very complete. We have Xyland's terrain editor that's been around for a while. There is another person who is working on a terrain editor that looked really good. Can't remember their name, but there's at least 3 or 4 terrain editors in Godot that are fairly full-featured, and again, the Tokushima games, or Tokusan games, I think they're called. Their terrain editor, for instance. This is not a person who just decided that one day I'm going to make a terrain editor. No, this is a person who decided I'm going to build a game, and this game needs a terrain editor. So this is a terrain editor that has been battle tested to make an actual game. And that game is a really beautiful game. And I don't think it's released yet, but it's pretty far along. So I always think that when something like that comes out of a real project, generally speaking, they're going to be far better than just someone building something because someone tells them to build a terrain editor. So that is that. When we look at GD extension, GD extension in the core is a very strong system. What GD extension currently needs is simply to mature. And it's slowly getting better and better, but there's still a lot of rough edges. At the core, however, it can do almost everything that it needs to do. It just, you have to sometimes work around some of the idiosyncrasies that it has. And again, that is also proven by the fact that there are more and more plugins out there that actually are full features, and like the Jolt Physics plugin, for instance. As far as the ecosystem around it is concerned, we still have a ways to go. We have the asset library, this beautiful thing, that was implemented 4 or 5 years ago, something like that, and hasn't really had much improvements since then. It's really great for discovering plugins, but it doesn't have any support for making sure that you can update when there's a new version, or if there's dependencies between different plugins, that it handles that. So there's quite a few things that still need polish, and it's kind of been held off because there's been a long-standing wish to move from the asset library to an asset store that both allows us to present free stuff, but also gives people the ability to sell things. So I think that was announced by Emmy a couple of days ago that there are now more solid plans in place. But how fast that's going to eventuate, there's a lot of legal stuff to go through. I know that there's people who have started stores, but we want to do it right. We want to make sure that we follow all the laws and rules around privacy, around piracy. So there's a whole bunch of things that need to be taken care of. Baby Martin, there is a risk there, indeed. Obviously, we are moving more to a situation where we want to be a little bit careful with what goes into core, and what we rather have implemented as a plugin. And there are risks with both sides of that argument. Like you said, if there's a whole bunch of different plugins to do the same thing or almost similar things, where are you going to be as an end user? What happens if a plugin gets, loses their maintainer? How do you even know whether a plugin is good enough for you? How do you deal with a plugin that's no longer compatible with the latest version of Godot, etc., etc.? So, so that's one side of the coin. The other side of the coin is the same goes when things go to core. It's actually been a really big problem for us over the years, that things have been added to Godot because a small group of users needed it. And it was then added by someone who did it in their spare time, or because they were working for someone who needed it, or whatever. And that person moves on, and now suddenly we have a system in Godot that nobody maintains because it's an edge case system. And that's a bigger problem for us, because now all of a sudden we have a mandate to maintain it, and we don't have anybody with the know-how because the person with the know-how has moved on. So we have a choice to make whether something that is added to Godot is something that we can actually maintain. Because nobody's going to be happy with a broken piece of software inside of our engine because it was made years ago, and it's kind of still sitting there and sort of chugging along, but it doesn't really work. So yeah, so those are the two sides of the coin, and I think it's always a point of looking at pros and cons of choices and seeing that no choice has only got good sides. And it is a matter of looking at the bad sides of a choice and seeing how can we manage those. And in no ways is Godot yet at a point where we know that if certain things go into plugins that we know how to manage it. That's something that needs to evolve. So, and again, that goes for both systems in core and systems in in plugins. The bottom line, I think, though, is, and this is common to all FOSS projects, and this is also where FOSS projects either become successful or they fall over, is when a FOSS project is still relatively small and there are a lot of parts of the FOSS project where there's only one person who is knowledgeable and working on that, then if that person moves on, things start to fall over. But as a FOSS project grows and you get a wider base of people who are working on it, there is less and less chance that that things become abandoned, because there becomes more and more overlap as more and more people get involved. Plus that, again, it's a game engine. Everybody in the community is making games. Everybody in the community is looking at these features and starting to use these features. So that, again, the 5% rule, if 5% of those people start contributing or start maintaining, the larger, the more successful a FOSS project becomes, the larger the group of people who are using it, the larger that group of people, that 5% of people who were actually maintaining things become. So, and when I look at Godot and I compare it to other FOSS projects, I think that Godot is right on that cusp. If you had asked me 3 years ago, we were really at risk. Like, if Juan 3 years ago decided that he had enough and walked away, Godot would probably have died, because while there was a sizable community on the rendering side, it was mostly Juan. Maybe 3 years ago is too soon, maybe 4 or 5. Because since then, I started helping out with Lawn Jelly, we have Ansir, we have Clayjon, we have, Dario and Mateos are pretty new. But over those years, we had quite a lot of people who stepped up. And while they still had some catching up to do on understanding the internals of the rendering engine, if today Juan said, I've had enough, I'm going to purely concentrate on W4 games, and I'm not going to, we'll be okay. He's not going to, by the way. He loves what he does, and he's going to be around for a long time. But if he would go away today, Godot would continue. So we've already reached that level of critical mass. We now need to get to a similar level of critical mass to make sure that edge case systems survive. And XR is a good example of that, by the way, because up until about 2 years ago, it was just me. So if I had decided I had enough, then Godot XR would have probably just hobbled along and maybe even died. Now all of a sudden, we have David, we have Malcolm, we have I don't even know what his real name is, something in the M. His handle's digital. But more and more people who are Fredia. Let's not forget Fredia. He's been instrumental in lots of things when it comes to XR support. We're slowly growing to a point where we have less and less to worry that if we lose someone, that someone else won't pick up the slack. And that's only going to become bigger and bigger and bigger. And the same goes for plugins. When a plugin gets successful, more, especially if the plugin is FOSS, the more and more people become involved with the plugin, the more solid it becomes. And that's going to be the big way off. The feature of intercompatibility, it is their terrain stuff, interactive world, partition, and but Paper Martin, and indeed, you're absolutely right for Unreal. But again, keep in mind that Unreal is very vertical in that way. you don't need that integration of a terrain system when you're making, a 2D Zelda game. Just as a crazy example. And I think that's where Unreal is really strong. They concentrate on, this is a type of game engine we built, and obviously the use is very wide, but it's still, the engine is far overkill for a lot of purposes. And if you want to go in a very different direction, then all of a sudden it starts finding you. So, and again, that's my impression from what I've heard. I'm not an Unreal guy, so the biggest thing for me in Unreal is that I do believe that the people behind Unreal are on a completely different level. So I have great respect for what they've done, but I also believe that there are a number of things in the indie game, especially in the indie game space, that Unreal probably isn't a very good fit for, no matter how good they do it. And it is because they are, very specialized on certain areas. Thank you. Yeah, no, we're pretty proud of XR Toolkit. Although I was talking to Z the other day, who made the really good point, and I believe in that too, is, XR Toolkit is really great to start, and for a lot of people, especially people who don't want to do the hard yakka programming, but more want to just put games together, it's really, really good. But I also believe that for people who want to do something special, learn to build it all from scratch, because there are constraints on a toolkit like XR Tools, especially because we want to really keep it easy to use. And that means that some of the more difficult things we're going to keep out of it, because it just becomes too complex, and that just means that it becomes harder to maintain, and that's just not what it's meant for. So 300, if you do pros, cons, balance, and it makes more sense. Well, yeah, that's really the philosophy behind FOSS. When you are using a commercial product, you pay what they want you to pay. And with FOSS, we always say it's free, and yeah, you can use Godot and never pay a cent. You can make $1 million with your game and never pay a cent to Godot. And if that's what you want to do, fine, it's your choice. But you can also decide to give back and say, hey, I have had my success because of Godot. I would have paid 5% to Unreal if I had made this successful in Unreal. I'm going to give some of that money back. And that is actually where more and more of our bigger contributions are coming from. Is, and I always say it takes 5 to 7 years to make a good game. And Godot isn't that old. Well, it was open sourced in 2014, if I recall from memory. And for a long time, it was an engine that was mostly focused on 2D. And again, needs, right? When you look at Juan originally making the engine, he made it as a 2D and 3D engine. Actually, if I understood correctly from talking to him about this, originally 3D was more important than 2D for him. But for whatever reason, and I think it is because, that's where a lot of indie developers started, because it's much easier than doing 3D games, is they started using Godot for 2D games. So all through the development of Godot 2, 2D got priority over 3D, because the majority of people making Godot games were making 2D games. And what you then also are seeing is that now that, Godot 2 was... Well, when I started 7 years ago, we just were about to release Godot 3, I think. So go another 3-4 years back. So you're now indeed seeing, for the last 4 or 5 years, you're starting to see really solid Godot 2D games that have gone through that whole development process. And I'm not talking about the little, jam games that, someone then perfects over a year time and then release. I'm talking about the really, properly thought out games that have long storylines or, dozens of levels or things like that. So you're seeing that all on 2D. When you're looking at 3D, it wasn't until Godot 3 got released that people really started to see that Godot was a potential option for 3D games. And we're then talking 7 years ago, and 7 years ago, we're talking about a handful of people choosing Godot to make 3D games. Those people are now coming out with their games. So TaleQuest is a very good example of that. A game that, when I started with Godot, was already in development, and then finally came out a little while ago. Game made by 2 people, very cute, very cool. And that's what you're seeing right now. Now you're starting to see those games coming out that were started with Godot 3. And the same is going to start happening with Godot 4, where more and more people start using the engine, but it's going to take a while before those people start putting the engine in the market. And then it'll take a little longer before they actually start making good money with what they're doing. And you're seeing more and more of those people then saying, I've made a pretty good bit of money with Godot. I'm going to invest, quote unquote. I'm going to donate some of that money back because I now know that that money will be well spent, and I'm going to make my next game in Godot, and that version of Godot is going to be better because I know that more people could work on it because I donated. The other example that I often say is donations from vendors. It is in the interest of vendors who want to have games run on their platform to invest money back into game engines, because the better the game engine is, and the better the game engine runs on their platform, the more games are going to be made for that platform, the more hardware they sell, or the more games they can sell on their stores or stuff like that. So it really is a matter of not demanding money from people. It's saying, hey, if you can see that putting a bit of money in Godot improves this game engine, and you're going to have a return on investment in that, in the sense of more games are, you're going to be able to make more and better games because of it, or people are going to make more and better games on your platform, or things like that. It really is something like, here's a game engine that everybody can use, and there are people who have an incentive of giving money when they are able, instead of turning it around and saying, like, you have to pay us money whether you're able or not, whether you're profitable or not, doesn't matter. You've reached a certain threshold, go pay up. So yeah. All right, where are we? Because it's already 1 o'clock. I'm going on. I can't keep up with the things. Where am I? Who in their right mind would do small 2D mobile games? Really, exactly. Maybe one way to it would be to have a standard code interface established by like or plugins as maybe. I think one of these things, when we're looking at problems like this, you can try and design this up front as much as you can, but in the end, the plugins are going to be built by people who are going to build those plugins so that they fit their needs best. And on one side, that means that they don't want to be held down by a system that stops innovation because it's been designed before we really knew what we needed, versus that if they start building these plugins and they start seeing some success, they are also going to start seeing what other plugins their plugins are going to be combined with. Or maybe, they build a suite of plugins, and they're eventually going to build a level of interoperability. Jesus, like I said, I'm not an English native speaker. Into those plugins. And I think On the short term, that's going to be a pain because yeah, you're going to get into a situation where you download, you know, a plugin from vendor A and you download a plugin from, you know, hobbyist B, and you download a plugin from, you know, maybe one of the core plugins, and they don't want to work together. That's possible. And that's annoying. But I also think that we're not there yet. You know, right now, it seems to be working. Let's say it that way. And I think that just needs to grow organically. And again, you know, it's one of the big differences I think with a game engine like Unity or Unreal is, again, the fact that it's FOSS. It's all public. So it's not about, you know, a couple of people who are thinking that they know best, but they don't actually have experience out in the field, designing a system and then pushing that system onto the world, and then finding out that nobody really likes to work with it because it's not really, it doesn't fit the reality. While in FOSS, most things are battle tested because they are being built by people who are actually building games. And that's, again, that's something I just can't stress enough. That is where, and it's not just Godot, it's with all successful FOSS projects. You know, all successful FOSS projects eventually get a critical mass where they blow past their competition because functionality is driven by market need, not by you know, whoever cries loudest that, you know, Unity, you have to add this, you know, because if you don't add this, then we're not going to buy your product. No, Godot doesn't care about that. Doesn't care about if people want to use it or not. It's there for the taking. If you like it, use it. If you don't like it, sure, fine. We'll sleep good at night. You know, you don't have to like our product. But it means that people who pick up Godot and start working with it and then come to a point where they also want to contribute, they are contributing changes that are needed to produce a game. And that has a sort of self-improving element to it. So I think in the long term that will be all right. But we'll see. Patrick, the mobile market is strange. The more I do stuff in that arena, the more I'm not quite sure where they're going, because there seems to be a need, and I kind of get it, because, you know, it's kind of part and parcel of the form factor that they have. They need to do things differently than how we do things on desktop. And I can't remember who I had a discussion with the other day, but it's one of the problems that we have with Vulkan is an open standard for graphic APIs, and it's tried to sort of brush over the difference between mobile and desktop. And it's kind of tried to put a layer on top of it, so that you can write code that should run optimal on both, and it doesn't actually work, because they are, you know, they're night and day. They're very different. However, at the same time, I believe that we are making so much progress on that front that at some point in time, mobile devices don't have to be different than desktop devices as far as the hardware is concerned. So I really hope that day comes soon. First version of Godot was released in 2001. Yeah, no, I was talking about the moment when it became Godot, and it was actually open source, and I think that was in 2014 from memory. Before that, yes, it was. You know, it has a long history. You know, it started as you know, an evolution of engines made by Juan and Ariel for, you know, for use mostly in the Argentinian market for people to build games with. So originally more following the same path as ID Tech and stuff like that. Is they build an engine for a game and then they sell the engine for people to make other games with them. And I don't know the exact history from the top of my head. But from what I understood is that they got to a point where they were both contracting for various game developers and working more on the software that those games were running on than on their own engine. That they had a choice, either give it up or open source it, and they went for open source, and then it took off, and Juan suddenly went like, this is actually more fun. I just want to work on this and make it better instead of and this is the thing that I really don't get is there's so much online about that. Juan is just after the money and da, da, da. Here's a guy who open sourced his software, worked on it for many years, earning very little money, while he had contracting jobs and offers left, right, and center. And even now, it's he's really in this because he loves the product and he loves what he does. That's really what it boils down to. For MB, that's I think the way that things always work and should work. Is you can think things through for decades, and you'll just find that you build something at the end after so much consideration that doesn't actually work, because it's much better to just make a plan, get there, try it out, put it in the market, see how it does, and either people like it, people don't, or people start getting feedback, hey, why don't we change this, why don't we change that? And as long as you're willing to evolve it, you'll eventually get to a much better place than if you try to think out every possible iteration and problem and thing. And again, that's why I believe in FOSS, because I think FOSS is the embodiment of that. Is FOSS is about I'm making something and I'm putting it out there because I know that if other people start using it, first of all, nice, feel good. I've done something. I don't need to make money with it. Let someone else enjoy it too. But also, at that point in time, other people are going to look into it and they're going to start improving it, and suddenly my product becomes better because of the improvements that other people have made. Again, the whole concept of it is Godot is a tool to make games. It's not the tool that makes money, it's the games that make money. So the more people make games with my engine, and the more of those people contribute and improve my engine, the better the engine gets. And before you know it, you have thousands and thousands of people contributing improvements. Can you imagine what that costs if a commercial company needs to hire thousands and thousands of people to work on something? And, the scales are, once you hit that critical mass, once you start growing beyond that scale, you become unstoppable, really. It's and that's what we see with many really big FOSS projects, whether it's Linux or Postgres, and even Blender, I would say. Although Blender is a bit of a weird case, and I'm saying that with all love and all goodness, because I love Blender and I love what they've accomplished. But Blender is one of those mysteries for me. FOSS for me is the more games. Again, good example. Everybody who makes games are developers. You need to be a developer to make a game. So everybody who uses Godot to make their game is automatically someone who has the skill to contribute to Godot. So the more successful Godot is, the more games are being made with it, the more people are making games with it, also the more people who contribute. Blender is different in the sense that here's a tool that is primarily for artists. So primarily there are people who start using the tool who do not have the skill to then go and improve the tool. And that, in FOSS land, that's weird. Like, okay, where are the developers coming from who are actually building and improving this FOSS product? But of course, the missing link there is Blender got its success because they got popular in the game industry, and especially with people like us who are indies who usually wear 300 different hats. So you have a lot of people who are not just the artist of the game, but they're also the developer of the game, and they're also the 3D modeler of the game, and then they're the guy who was making the music for the game. And I guess that's where Blender got its its bloom from, its contributions from. So well, for me, Firefox is actually also one of those same conundrums. It's the same thing what I just said for Blender is the majority of users of Firefox are not developers. They're normal users, normal PC people. So they don't care whether Firefox is FOSS or not. They just care about the experience. And if Firefox doesn't do it well, they're just going to go to another browser. They're not going to go back and say, hey, Firefox, this isn't working. Oh, Firefox, you're FOSS. Oh, let's go and contribute to Firefox. So, like I said before, in Godot land, you might get 100 people using Godot, and 5% of those people are going to start contributing. And that's just a number that I just picked out of the air. It might be much more. But with Firefox, you might have 1 out of 10,000 people who might start contributing, because the other people just see it as a tool that they use, and they don't have the skill to do anything to improve it. Well, Paper Martin, that's actually one of the things that I find very interesting. And that, again, sort of underlines the thing that I was mentioning. Is, and one of the, I was talking on Twitter about this, one of the weaknesses of FOSS, right? If you look at FOSS, and the majority of development in FOSS is being done because people who use the product are developers and feeding back their knowledge and their expertise and building the things that they need, it also means that it's very function driven. I need this function. I don't care if this function looks nice or is easy to use. If the function works, perfect. And then I think that Godot is kind of special there, that we have a core group of people who are not okay with that. So while there is still a lot of stuff in Godot that could be much more improved in UX, we do have a lot more hesitance to add things that aren't at least a little bit thought out properly. With Blender, kind of the same thing, is that they were always fairly good at making sure that the contributions were at a certain quality level, but at the same time, Blender was focused on people who were more developer than artist, I guess. And even I noticed that, because I learned 3D modeling on Max, which I found, 3D Studio Max, which I found, and we're talking 20 years ago, by the way, which I thought, amazing. And then I switched to Blender, and I couldn't use Blender for the life of me because of how weird the interface was and how unintuitive the interface was. Fast forward 20 years to now, one of the things that we're seeing with Blender, and that we're also slowly seeing with Godot, is because it's grown to a certain point, you're starting to see that people who have a insight on UX are starting to find ground to help out. And I think with Blender, obviously they had the big Epic Mega Grant that they got that helped them, hire expertise in. And I think, because when you look at Blender 3, the UI is seriously improved compared to Blender 2. as far as I can tell, because again, I'm a hobbyist when it comes to modeling, but or 3D modeling, but I wouldn't say that I'm the target market for what they're doing. But I think that's changing, and I think the same can be said for Godot. Is we are getting more and more people with an eye for how to improve the user interface involved with the project. Now, there's still a disjoint between, people giving suggestions that actually work for the majority of people working with it, because there's, it's still hard to sort of put yourself into other people's shoes. And stereotyping here, most developers are stubborn as hell, so it takes a while to convince them from things that they themselves don't have an eye for. But I'm seeing a change there. I am really seeing that there is more and more input from people who understand UX, and I think we're slowly going to see improvements there. All right, Sin. Yeah, I made it way longer than I wanted. I should really be going to bed as well. But thank you for joining in on the stream, and I hope you enjoyed it. And yeah, I hope to see you again when we do another stream. For me, of course, I believe too that the Godot interface is vastly superior than Unreal and Unity. But yeah, I don't know. I'm a strong believer that those things are incredibly subjective. And again, it boils down to what I said before, is I don't believe in the best game engine idea. The best game engine for you is going to be a combination of can the game engine build the game that you want to build? Does the game engine in a way work in a way that is agreeable with the sort of person that you are, and can the game engine deploy to the platforms that you want it to deploy to? Although that one actually is yes for all game engines nowadays. But I think those first two are really the most important ones. It doesn't have the capability to make the game that you want, because this is the thing that a lot of people go wrong with. They're sort of like, oh, I don't want to choose Godot because I can't make Horizon Zero Dawn with it. Yeah, who are you? You're a single man band. You can't make it Horizon Zero Dawn. What's the game that you're working on? Oh, you're making a game like that. Oh, really cool art. You can make your game in Godot just fine. You don't need a better game engine. But if Godot allows you to make your game because it's easier to use and you can build with it faster than you can build in the other engine because it agrees with you, my point two, that the approach in Godot agrees with you, then that's what's important. That's far more important whether Godot is the fastest engine, or whether Godot has the biggest community, or whether Godot has a system that you might never even use because you don't even have a game that needs it. All right, let's see. Oh, dang. It's funny how I say I really have to go, and there's more messages. So Francisco, it will be necessary to create versions with reduced UI for education purposes. Godot intimidate students first. But yeah, that's that's a whole story on itself. Although again, I really recommend check out GDQuest. One of the brilliant things that he did was create a course for GDScript that is not done in the editor, or I think he uses Godot for it, but the course is actually online in a web interface where you interact with GDScript, but all the complexity is gone. So coming. But yeah, and I noticed that also with, for instance, my kids who, are getting things like what's it called, the Microsoft thing. Oh, I can't forget it. I can't remember what it's called. But yeah, the very simple little, put blocks together to create some logic things. It's cool, and they're loving it. They're figuring it out, and then they see me working on Godot, and they really sort of go like, I don't get that. I don't want to build a game in that. Although my son's slowly starting to catch on things, which is kind of cool. Although he's not very interested in game development, his friends are, which is fun. So Chris, yeah. Thank you for joining. Thank you for lasting for the almost 5 hours. I can't believe that we've gone on for 5 hours. 4MB, thank you for joining. I hope that that you really enjoyed it. Thank you, Felipe. Yeah, Paper Martin. Thank you also for joining. I'm gonna put an end to it. It's 1:30 here, and I need to wake up at 8 tomorrow. So yeah, cool. Yeah, thanks everybody. I hope you all enjoyed it. I definitely had a good time. I'm glad I did this. So yeah, we did over 3 hours of poking render effects, you know, putting it apart and looking into it, and a good 2 hours just chatting, which is actually really nice. Yeah, I hope I was able to make sense, and especially because I'm kind of getting tired, so I hope I made sense when in my sleepy state. But yeah, enjoy it. Thank you everybody for being here. We're gonna do this again, and we'll pick it up from there. So good night, everyone.